And for those who enjoy this channel and would love to support us financially, please feel free to hit that donate link. We'd greatly appreciate it. God bless.
Awesome. Thanks so much. Yes, we're live tonight on Standing for Truth. We got a really fun discussion ahead of us tonight. We've got Salvador and Snake was right, and they're going to be discussing. It's going to be more of an interactive discussion. So I think it's going to be a lot of fun. It's going to be a little different. Like I said, we got Snake was right and Salvador. They're going to be discussing structural biology versus abiogenesis and evolution. But before we get started, I want to thank especially Sal for joining us today because it's his first time being with us, hopefully the first of many. So we're really looking forward to having you on again as well. And Snake as well, thanks so much for joining us. I do want to give you both just a minute or so, just give us brief introduction as to, I guess, your position, what you're doing on your channel, just a little bit about you. We can start with you, Salvador.
Oh, thank you for having me, and I'd like to also thank my counterpart, Snake. I'd like to acknowledge my Lord and Savior Jesus Christ. This evening, I will be talking mostly about just the science of abiogenesis from a critical standpoint, one that would be favorable to creation. I don't consider myself a scientist. I'm just a troublemaker. And I presently do reporting work on the areas of molecular biophysics for Dr. John Sanford's foundation. And part of my role is to just kind of keep my eye on the various peer-reviewed literature out there. I have been going to the NIH to learn about junk DNA and the ENCODE project and the 4D nucleome and PsychEncode and REMIC and all these other things. And then I work with I work on reporting and occasionally helping write papers with some of the ID-friendly and creation-friendly scientists who teach at accredited universities. So that's a little bit about me. And thank you all very much for giving me a chance to present this evening.
Awesome. Well, thanks so much. It's an honor to have you here. We're all big supporters, and we respect Dr. John Sanford a lot. So, that's awesome. Thanks for the intro. Let's hand it over to Taylor. Take a couple minutes. What's going on?
Howdy, y'all. Well, my channel kind of focuses on various interests. Been going through a creationism phase this past year, but I started out kind of debunking some myths about medieval sword carrying, and those are to date my most successful videos, but I kind of just go after whatever I feel like going after at the time. I'm going to start going into debunking some political myths like Russiagate and stuff like that. And one of my big things, at least on Facebook, I kind of got away from that because I sucks up too much of my time. But I debate a lot of communism on Facebook, so I used to be a communist, and so I want to start making videos about that kind of stuff, debunking communism and kind of, you know, the principles of capitalism, and other political things. But I'm working on a molecular, cellular, and developmental biology degree, so I really like to focus on biology-based topics as well. So that's why I'm here tonight.
Well, that's awesome. Thanks for being here. I mean, this isn't your first time. You've been here many times, so you're no stranger. And that's good. I mean, you both are very knowledgeable. That's why these discussions are so enjoyable. So we're all looking forward to this one. Yeah, like I said earlier, it's going to be more interactive. And since it's going to be Sal, who's looks like mainly kind of going through his slides, going over his position, and we're going to have Snake here critique it. And I mean, it may just go anywhere. I think it's going to be a lot of fun. But since I guess Snake will more so be on the side of evolution and abiogenesis, of course, and Sal is defending structural biology. Snake, I want to give you just another minute or two. Just kind of like what your position is. I mean, we all kind of know, but like what you might feel some of the evidence is, or some of the data that kind of convinces you, and take your time.
Well, should I go first? I think evolution is a pretty well demonstrated fact at this point. And it seems like we're going to be focusing more on abiogenesis tonight, which I just believe is it hasn't been as demonstrated as evolution has, and so they are separate topics. But I think that it is the most scientifically backed hypothesis we have so far. And so if there's anything better than that, I'd like to know about it.
Awesome. Okay. Thanks for that there. Snake, Sal, let's hand it over to you. I imagine you're probably going to want a screen share, and we will kind of go from there. We've also got John Maddox. John, thanks for joining us. John and myself are both going to be controlling this conversation, making sure that it goes smoothly, but both Taylor and Sal are both respectful individuals, so I don't think you're going to hear much from us, but just in case, that's what we're here for. So John, thanks for being here too.
Yes, thank you, John.
Looking forward to it very much. This should be a very interesting dive into things that I find extraordinarily fascinating. You know, on the well, I'm going to turn it back over to Sal because he's the expert, and I want to learn from him. So it should be fun.
Thank you again. I'm going to be going at the origin of life differently than most creationists or ID proponents. I actually will not be trying to defend the ID position or the creation position tonight. What I will be doing is just reviewing with critical thinking and critical analysis the current state of affairs. If we assume that our present understanding of basic physics and chemistry is mostly correct, the origin, my hypothesis is the origin of life would be a miracle in the statistical sense. Whether such miracles are miracles in the philosophical or theological sense is not the focus of this presentation. Just a little bit, I didn't mean to be inflammatory. Well, maybe I did. I used the word evolutionism. That word is actually used by Theodosius Dobzhansky in Apinas. Proceedings of American Philosophical Society. And even the word evolutionist is used by a population geneticist by name of Joe Felsenstein. But let me just move on. I'm going to start out with something from a secular perspective. This is from The Origin of Life and Evolution of the Biosphere. It's a journal. And this is by Steve Benner, who is actually researching abiogenesis. He's not a creationist, but he's had this to say. He said, the asphalt paradox an enormous amount of empirical data have established as a rule that organic systems, given energy and left to themselves, devolved to give uselessly complex mixtures, quote unquote asphalts. Theory enumerates small molecule space as well as structure theory in chemistry can be construed to regard this devolution a necessary consequence of theory. The next slide is just kind of, it brought to mind pictures from Raiders of the Lost Ark, so you'll have to forgive me. This really has nothing to do with anything, but that's what came to mind when I saw this quote. Benner has another quote in the same paper. Thus, even if we solve the asphalt paradox, and there are other paradoxes, by the way, the water paradox, the information need paradox, and the single biopolymer paradox, we still must mitigate or set aside chemical theory that makes destruction, not biology, the natural outcome of our already magical chemical system. So that right there summarizes what I'm going to be talking about. Only part of what I'm talking about today. But I wanted to give kind of a quick overview of actually where I'm headed. This is a photograph of the NIH's Evolutionary Genomics Group. I don't know if you can see my cursor. This is Eugene Koonin. He is one of the top evolutionary biologists in the world, something like 400 publications. Obviously, that's hard for one person to write. He has this whole team of about 30 people. One of them in the photograph was my professor of bioinformatics, who taught me a little bit of evolutionary biology. What's interesting is he's one of the tops, and this is what he had to say about the origin of life. This is from his peer-reviewed article, The Cosmological Model of Eternal Inflation and the Transition from Chance to Biological Evolution in the History of Life. That's a really long title. So I'm just going to read what he had to say. Despite considerable experimental and theoretical effort, no compelling scenarios currently exist for the origin of replication and translation, the key processes that together comprise the core biological systems and the apparent prerequisite of biological evolution. The RNA world concept might offer the best chance for the resolution of this conundrum, but so far cannot adequately account for the emergence of an efficient RNA replicase or the translation system. The MWO, which stands for Many Worlds in One, version of the cosmological model of eternal inflation could suggest the way out of this conundrum, because in an infinite multiverse with a finite number of distinct macroscopic histories, each repeated an infinite number of times, emergence of even highly complex systems by chance is not just possible, but inevitable. So that's rather interesting, because if he's invoking, I'm going to just deviate a little bit from science here. I just have to make a little philosophical comment. If he's invoking infinite multiverses, which you can't see, which you can't test, which you can't prove, that's not exactly science, in my opinion, and it doesn't look too much different from any other. It doesn't look that much different than invoking God, in the sense that it can't be, it's not directly testable in our present life, or not observable, not repeatable. And I'd also say that if he's invoking infinite universes, does that guarantee that in one universe that special creation happens somewhere? So his solution, the reason really that, however you interpret this, my point is showing that this is the current state of affairs with abiogenesis. Not everyone is that pessimistic as maybe Benner or Koonin, but that is in contrast to where it was when we had the Urey Miller experiment, I believe, like in the 1950s. And at that time, shortly at that time, there was a lot of excitement. At that time, this is a quote from George Gaylord Simpson, said, "The consensus is that life did arise naturally from the non-living, and that even the first living things were not specially created. The conclusion has indeed really become inescapable, for the first steps in that process have already been repeated in several laboratories." So does anyone have comments so far? I'm just trying to give a contrast for where we were about 60 years ago compared to today.
Of course, yeah. Why don't we? I guess every couple slides. I know it's been a few. We will hand it over to Taylor. If you want to take a few moments to kind of give your thoughts, or maybe you have some objections to what Sal is saying, and we can. I guess I should say anything that you see pop up. Don't feel obligated. Like you don't have to interrupt real quick if you have something you want kind of to touch on there, Snake. So take it away, Snake.
Yeah, so my first impression would be, I guess, starting with the asphalt problem. If I'm not mistaken, it seems like this has already been solved, since we have various undisputed experiments that show how we can get complex organic molecules from basic chemistry that's less complex than the outcome. So I don't, unless I'm not understanding the problem right, then that's already been solved. And then basically saying that we see decay sometimes and therefore it's the universal law. It happens all the time. That this is, to me, is a cherry picking fallacy, again, because we see various chemical reactions that do become more complex. And and then I guess the final point would be that, yeah, there are some scientists who think that various gods did this or that, but at the end of the day, this is without a god to point to. This is basically the god of the gaps fallacies, which is an argument from ignorance, and so it's just saying we don't know how this happened, therefore a god explains it. And the reason why I am hesitant to go with these arguments is, I mean, one, it's a fallacy, but we've learned throughout history, like we used to not know what lightning was, and yeah, we had no scientific explanation whatsoever for it. But that doesn't mean that we can just assume that Zeus creates lightning just because we don't have an explanation. Just because at the time that might have seemed like a more plausible explanation, but that's because it's an ignorance fallacy, and it's explaining something with a god is no more an explanation than magical pixies as an explanation, or magical anything, or aliens, without having something to show for it. You can postulate some hypothetical thing that has in its definition the ability to solve the problem you're looking at, but that's just begging the question and circular reasoning. And even if we could grant that abiogenesis was a miracle, and we could even accept that God created life and maybe was responsible for this miracle, but that doesn't really discount any of the evidence of what happened afterwards. So those are my thoughts so far. If you want to pick out any of those to further discuss or keep going, or
of course, yeah. Let's hand it over to Sal. If you guys want to have a bit of a back and forth on those points, I'm happy with that. Take it away there, Sal.
We clearly disagree on I think on the state of affairs. I actually think the cherry picking is looking at a few isolated experiments where something simple becomes more complex. The general rule is devolution, and we don't have to try to settle it today. I'm just going to say, why don't we? I'm just going to put it on the table. There's the references there, and then I'm going to actually go over some more papers and considerations. And I'm interested for the listeners and audience. They can fact check or fact search what I'm going to put on the table today. So rather than try to settle it in a couple minutes, maybe we agree to disagree so far, and I'm just going to move on.
Well, I just have one quick comment about the cherry picking. So if the claim is that everything decays and that we don't have instances of something becoming more complex, all we need is one example of it happening to kind of disprove that.
I'm not claiming that it never becomes more complex. I'm claiming that is the general tendency. It's a pretty strong tendency. And I'm going to actually argue statistically how strong that tendency is. In fact, if I state probabilities here, I'm probably going to even understate it. So, it does raise a philosophical question. And at what point will someone accept a miracle? And I'm not gonna fault someone for saying no. Let's just keep setting the bar higher. And I totally respect the atheist viewpoint or the agnostic viewpoint, because unless someone has experienced the miracle in their own life, the natural tendency is to expect that natural things explain things. So I don't fault them for that. And I'll share something really, really personal. We live in a world that has a lot of problems, and sometimes it's really hard to think there's a God out there that cares and that is trying to, set things right. I'm sorry to have to share this, but I'll just, I know there's a lot of hurt out there. I had an aunt, her name's Connie Reyes. You can look her up. She was raped and murdered in the 1990s. It was just tragic to our family. And so I totally understand, and I totally get that people can, reject God for a number of reasons. And sometimes it's very personal. So I'm not faulting anyone for being a methodological or philosophical naturalist. That's between them and, what they believe. All I'm here to do is just try to go over the statistics. I'm not going to try to prove creation. I'm not going to try to prove intelligent design. I am going to try to survey current literature. So, I just want to totally empathize with anyone who's like, they're going to disregard the possibility of a miracle. So,
okay. I did want to make clear that abiogenesis is not necessarily atheistic. That it is compatible with a lot of theistic hypotheses. So I'm not necessarily here defending atheism, just what I view as science.
Yes, thank you for that correction. So I'm gonna just move on. Is that okay, Snake? Can I call you Snake, or how should I address you?
That's fine. Yeah. Go ahead.
All right. So this is where we left off. Now, the material that I'm gonna go through, and only a fraction of it today, it's from this book that was published in March. I don't know how many of you are aware of it. It is called The Stairway to Life. It is available on Amazon. And you can probably see this is all the steps that have to happen to reach life. And I'm not going to get immediately in the argument if it all has to happen at once, but it has to happen somehow to reach it, because these are all the parts of life, all the systems that have to work to be in place to get here. The argument is whether we can get this partially and kind of build up from it. But anyway, about the authors, Dr. Change Laura Tan, changes, and the way it's pronounced in Chinese is something like Shanggu, but I can't pronounce her name. She received a BS in chemistry from Hunan Normal University, an MS in organic chemistry from Nankai University, and a PhD in biochemistry from the University of Pennsylvania, and also completed a postdoctoral training in genetics at Harvard Medical School. She's an associate professor of biological sciences in the College of Arts and Science at the University of Missouri. That can be fact-checked. And Dr. Tan then is an Ivy League. She is a creationist. She wasn't a Christian. She was actually an atheist most of her life. She came to the United States and became a Christian, and she has a very interesting story. Her co-author to that book is Dr. Rob Stadler. He's also an Ivy Leaguer. He received a BS in biomedical engineering from Case Western Reserve University, an MS in electrical engineering from MIT, and a PhD in medical engineering from Harvard MIT Division of Health Sciences and Technology. As a scientist in the medical device industry for over 20 years, he has obtained more than 140 U.S. patents, has been elected fellow of the American Institute of Medical and Biomedical Engineers, and has contributed to medical devices that are implanted in millions of patients worldwide. So some of his inventions are inside the bodies of millions of people today. So that's a little bit of background from where I got this material. I'm indebted to Dr. Tan and Dr. Stadler. So this is the Stairway of Life. I kind of put it in reverse order here. This is really the first step, and then these are the final steps. I'm not going to cover all that today. I'm only going to cover these two, the homochirality of building blocks and the consistent linkage principle. So when we said this is going to be only 45 minutes, an hour, whatever, you can imagine all the other steps are going to be pretty, it's going to be, if we actually did this even in halfway detail, this would be a 12-hour discussion. So that's what I'm going to cover. And there's the stairway there again. I'm going to start with improbability. A lot of creationists and ID proponents, I don't think, properly do improbability. And I'm going to use a basic probability concept called the law of large numbers. So according to the law, I'm just going to read it. This is from Wiki. There are various versions of this, but this is the Wiki version. According to the law, the average of the results obtained from a large number of trials should be close to the expected value and will tend to become closer to the expected value as more trials are performed. And that doesn't apply generally. It applies to things like fair coins. Not every object is subject to the law of large numbers. But if we flip a coin, the expectation, if we flip it 1,000,000 times, all the flips, if we tally the number of head flips versus tail flips, it'll approximately be 50%. And if there's some deviations from that, that's okay. It's fair enough for our purposes. Now, that actually applies, I'm going to argue it actually applies to things like the origin of life. And I'm going to elaborate a little bit more on that. So I'm going to say it is relevant to here. And just to point out, I'm not the only one to tie the law of large numbers to the origin of life. You'll see this is a paragraph from this publication says that this is a consequence of the energy degeneracy between the enantiomers and of the law of large numbers acting in the thermodynamic limit. In summary, chiral statistical fluctuations around a stable racemic configuration cannot be amplified. And there's another one here. Another paper also uses the law of large numbers. I'm not going to read it unless you're really interested, but I'm actually going to cover it a little bit in this talk anyway. So I'm pointing out here that I'm not going out on a limb by invoking the law of large numbers. So let me review a little bit of the law of large numbers. And then I'll pause a little bit and we can discuss this. So what I want to do is just go over the idea as it applies to coins. We can argue later how much it applies to biology, but I think I've at least established a connection with biology. So if we have these, if you saw a configuration like this on a table, if you saw these coins, granted all these coins are designed, but the question is the configuration the result of chance? The law of large numbers would question that because the law of large numbers would say it should be a little bit closer to 50%, like not 100% heads. Does anyone have a problem with that? If I said this is not the result of a random process? Okay. Hopefully no objections. Now, yeah. I want to say not all, I have to emphasize again, not all objects are subject to applying the law of large numbers analysis. You can't do this with a two-headed coin. It will not work. We have to use object with a discrete outcome, but it's dynamically unstable. So we have fair coins, dice, dominoes, playing cards, etc. I want to talk, it applies to physical objects, not conceptual objects like binary numbers inside a computer. And I'm going to argue that biological and chemical phenomenon in a random prebiotic soup are subject to the binomial distribution and the law of large numbers. That's the part that's going to be probably that will be debated, and that's okay. This is a little bit closer to 50% heads and 50% tails, but even then, I mean, you could see that this is still kind of a violation of the law of large numbers, because we have a region here that is just all tails. And there are even more subtleties to that. Let me show this picture. This is also a violation of the law of large numbers, and it will have some importance to the Homo-linkage principle in the biopolymers. But you could see here, all the heads here are pointed one way. See that? That is also a violation of the law of large numbers. That's a fine point. It might take a little work to make that argument. Now, when I taught intelligent design and creation science in an extracurricular class at college at James Madison University some time ago, I gave students an assignment. I said, I'd give them dominoes. I gave them dice and I gave them coins. And I said, just arrange this like you would in a way that if someone happened upon it, they definitely would think it was designed, at least by a human designer. Okay. So what do? So I saw things like this. Well, this is a violation of the law of large numbers because you should see a mix of all the numbers from 1 to 6. Instead, they're all 6s. So that means the dice had to be oriented in the right way. This one is not exactly a violation of the law. Parts of it are a violation of the law of large numbers. It's kind of hard to frame it in terms of that. But the point is we can state probabilities that are in terms of violation of some physical principle. And let me see. There are other things we can do, like this card tent, which is a precursor to a house of cards. We could say that the structure is not a probable outcome from random processes. I mean, like if you had just thrown them, it would be more likely lying flat. What you would not get is something standing up. This can't be easily or elegantly framed in terms of the law of large numbers, but it's still a violation of probability in terms of random processes. I should note, I mean random in the mathematical sense. I'm not talking about random in the metaphysical sense where you have to invoke things like non-intentionality or whatever. There's a way to frame randomness in the mathematical sense where you frame it in terms of things like distributions, like the binomial distribution, the normal distribution, etc. So are there any objections to what I've said so far?
Actually, before you speak, there's so you went over a lot of really good things. So we'll definitely give you ample time there, Snake, to express your objections and thoughts, and then we'll go back to Sal for a brief dialogue, or however you guys want to proceed. Go ahead there, Snake.
Yeah. So the objection that I would have is that they've actually run mathematical simulations of chiral enantiomers that can actually result in the selection of homochirality from these large numbers of racemic mixtures. So, and I haven't read the whole thing. I'm not. It's a lot of math, but they're reporting that they've actually been able to demonstrate this with simulations. So I don't think it's exactly miraculous. And I can give you the name of the paper if you want. There's a couple of these. It's called Spontaneous Mirror Symmetry Breaking and the Origin of Biological Homochirality.
Oh, if you're done there, Snake, you can you can respond, Sal.
Yeah,
all right.
And I think sorry, one more sentence, I guess. There are other papers too, which kind of narrow it down to it probably had to occur in a specific time in abiogenesis, so it would have occurred. It wouldn't have just been any. It couldn't have happened at any old time during the thing. So yeah, you can go finish.
I'm sorry.
You can go ahead and continue.
Oh, thank you, Snake, for your comment. I'll have to contest that. That's an example of cherry picking. And this paper that I referenced earlier actually points out the problem. They can find isolated instances where you have symmetry breaking, where it's going to be all like say left or right, which is analogous to heads or tails. But that's cherry picked because in a prebiotic environment, you have all sorts of catalysts there. So one catalyst might make it all left-handed, another right-handed. And when you average it all out, it still ends up being a chiral mess. The other thing that needs to be mentioned here, and I referenced this paper that also invokes the law of large numbers. It says in these chiral statistical fluctuations around a stable racemic configuration cannot be amplified. What that means is if you just leave these amino acids just to sit there in a pool, they're going to spontaneously change. They're going to spontaneously isomerize, and it's what they call a racemic mixture. This is analogous somewhat to radioactive decay. So if we just leave it out there, it's going to flip back to, so even if you started with all left or all right, in a matter of time that's not very long, it's temperature dependent, it's going to flip back. It's just like shaking a bunch of coins. So, but that's not the only problem. Chirality is only one of the problems, and these things have half-lives that it can stay homochiral for it can't stay homochiral for very long. So, but if we can agree to disagree for now and allow the audience to fact check these, I think that's the most we can ask. If it's okay, I'll just go on and.
Yeah, I just don't think it's cherry picking if the argument is that it's a miraculous type of event, because we can actually observe that it happens sometimes.
Okay, well, I'm gonna go on, and if that is that okay, Snake? Thank you very much for your comment.
Mm-hmm. Yeah.
So I wanted to point out, this is why I like structure. See, we don't have to invoke information theory to say this is an improbable structure. That's one of the reasons I like structural arguments versus information theory arguments. It's also very visual. I'm a very visual person, and that helps me to see things. See, like, let me see if I could show that college example again. See, these are structural arguments. You can see the design. We don't have to invoke information theory to say that these are design configurations. So my point in at least going this far was to say that there's some various objections to probability and statistics. One of them is called the Texas sharpshooter fallacy, or the fallacy of seeing clouds, faces in the clouds, like this one here. You see, that's the nose, that's the eye, it's kind of lips. Or what they call sometimes a single target fallacy, where there might actually be multiple targets, but we do our statistics based on one target. But what I was trying to illustrate with my examples, with the law of large numbers, etc., is these things are able to that this is one way we can avoid those fallacies. And the issue is whether we can apply it to biology. That's why I'm talking about structural things.
Well, I don't think you actually can apply those examples to biology, because the problem I have with using cards and dominoes and other inanimate objects as analogies for these complex organic molecules is these objects don't actually do anything. All they do is just sit there. They don't interact with the environment. They don't interact with each other. They're just rigid bodies. And or sometimes people use bricks spontaneously building houses on their own as examples. And again, the problem is bricks don't actually do anything with each other. They just sit there. But organic molecules do interact with each other. They actually bend and move. They cause reactions with one another. They cause each other to change form and shape and things like that. So I don't think that this is a particularly useful analogy.
Well, thank you for your comment. I'm going to actually go into some of the biological stuff and the biochemistry. As I said, I got this from a physical organic chemist. So this is at the stage here for readers that are not that familiar with physical organic chemistry, certainly not at the level that Dr. Tan is familiar with it. But anyway, my point is at least as far as structures like this, I hope people don't have a problem saying this is the Texas sharpshooter fallacy, that we think that this is improbable, or that it's a single target type thing, or that we're seeing faces and clouds. Do we have at least some agreement that these are improbable structures?
From a human throwing them on the table, sure.
Okay.
But I just don't think that they're very analogous to how molecules behave with each other.
Well, thank you for your comment. So I'm going to skip this slide. Miracles in the statistical sense. I'm not going to go there. So as I said, I'm going to show that we're talking about some of the molecules. This is the analogies that I'll be making for the homochirality. We have left-handed and right-handed amino acids, and it's corresponding to heads and tails. These will spontaneously flip states just based on chemistry and the collision and random actions of molecules. That's why it's temperature dependent. We also have chirality, even more levels of it, more than just heads or tails for nucleotides. I'm sorry, this is nucleosides, but we can add nucleotides to this and it'll even be more states, not just heads or tails. It'll be more like a multi-sided dice, not just heads or tails. And so the reason that they flip is we have in the liquid phase, we have molecules just moving around and colliding with each other. And as the temperature goes up, they move around even more. There are various kinds of motions involved. We have bending, we have stretching, we have rotation and translation. So stuff is just moving around because of the internal energy, which we sometimes call heat. So I'll call colloquially called it heat energy in the system. So that will cause the flipping of states in the amino acids. That's why even if we began with symmetry breaking where everything's left-handed, it's going to flip eventually to a mix of right and left-handed. And that's where I was arguing it's cherry picking to suggest that one isolated example will override what are very well observed laws. Now, the next point is homo-linkage. So again, I'm trying to go to some more everyday kind of examples where we can kind of see with Scrabble letters. I'm going to try to apply it to, this is a picture of DNA, part of the double helix. It looks kind of like a railway, and I will go back to that, and then also the various ways that it can link and not link. But so if we can pause a little bit, let me go back to kind of more everyday things. I'm going to use the word ledger, Heath ledger and accounting ledger, and start with the Scrabble letters. So if we have Scrabble letters here, you could see that they can be of any orientation. They can even be laid flat on the wrong, quote unquote, wrong side. They can be like upside down. They may not even be in a row. This is actually a problem at the molecular level. Let me at least try to illustrate it with Scrabble letters, and then I can talk about it at the molecular level. So at the Scrabble letter level, a Scrabble letter can be upside down. It can also, well, it can't do this. You see this? I made the D a mirror image. That's like a flip in chirality. You can't really do that with a Scrabble letter, but just bear with me. So, I mean, let's say it started getting into the wrong state. It can be flipped with the face down, and actually, the way this corresponds to what happens in DNA, this is an understatement of how bad it can get. I'm just kind of trying to illustrate it, approximate it with Scrabble letters here. And you could see that it's hard to even get it to line up. So I'm just going to fix that here. So you can see all the things that have to be done just to get it to line up, kind of like in a railway. I call it a railway, or just kind of straight, all aligned. This problem that we saw with the Scrabble is exactly the problem we have in the origin of life from a prebiotic soup. These things, what made it look so nice inside of a living organism where it's all nicely lined up, you see how it's all nicely lined up in a row, you even call that a backbone, and the other backbone on the other side. That doesn't happen naturally in a prebiotic soup, nor is it expected to be. And let me see. So we can cover that. Is there any questions so far with what I pointed out here with the Scrabble letters before we move on to the actual chemicals?
Not so far.
Okay, thank you. So Dr. Tan pointed out in box A is normal DNA. All we're going to do, we know that DNA has 4 letters. It's A, C, G, T. That stands for adenine, cytosine, guanine, thymine. This is, does anyone know what that is? I think that's adenine. Adenine, and this is cytosine. So the way this deoxyadenosine monophosphate, this is a deoxyadenosine monophosphate here. This is a deoxycytosine phosphate. I don't know the actual term. I'm embarrassed. This is the way it is in living organisms. But if we randomly just took kind of the possible configurations that it could be, say from a prebiotic soup, you can get a configuration like this, or like this, or like this. It's because there are all sorts of ways it can connect. And I have something that Dr. Tan said I could share. Maybe we'll post it somewhere, and if any nerd is really interested in the physical chemistry, it can be explored. But what she found, let me see if I have the slide. Yeah. So the problem is, if you could see this, this phosphate group here can be connected in all sorts of places. Let me see if I get another slide. Yep, here it is. This deoxyribose here, that's a very special kind. In solution, in a prebiotic solution, you'll get something like this. You'll get a mix of this alpha T deoxyribopyranose and the beta D2 deoxypyranose, and et cetera, et cetera. The one that's in life is this one. So if you just throw this in solution, you're going to get all 5. That's a problem. That's a problem. And so what ends up happening is you get all these different connections. And let me see. She calculated how many of these we'll get just for the parent, just for these 2 nucleic acids. Okay, so the human genome has 3.3 gigabases. We're just talking 2 bases between adenine and cytosine, and this is what she had to say when you do the accounting. It is striking that our desired adenine cytosine deoxyribose dinucleotides is just one of the 16,200 possible chemicals that could result from linking an adenine, a cytosine, to deoxyribose in 2 phosphate groups. There are therefore 16,199 possible wrong configurations and only one correct configuration of a single-stranded DNA molecule that has only an AC, adenine cytosine dinucleotide. Many of the isomers with the wrong configurations are energy equivalent to or even more stable than the correct one. So the one in living organisms is actually more unstable than what you would find that would naturally form, and that's a problem. Now, I just threw a ton of stuff. Her book is available, and I'm happy to share the part that she released to me where she actually does the calculations. It's about 5 pages long. So for the listeners who are organic chemists, they can scrutinize this. And even if she were wrong, about this number of 16,199 possible wrong ways. Let's say she's off by a factor of 10. That means there's still 166 possible, 162 possible ways approximately of going wrong. That's a lot. And that is the problem with the law of large numbers there. And she will go into her book, the one that's on Amazon. She'll describe some of the chemical experiments that try to override that. And that's why we need a lot of difficult processes to deal with that. So
I was just going to jump in there real quick, Sal. Since looks like we've gone through another few slides, a lot of points are brought up. Snake, if you feel like you wanted to touch on a few things and maybe have a brief back and forth on some of the points brought up, or even just some thoughts, you can do that now.
Sure. I mean, I think so. Basically, even if you have this system where some of the molecules will flip chirality, if this process that's breaking the symmetry in the first place is still intact, it's just going to keep pumping out the same homochirality. So you are losing some, but you're consistently making more and more and more of them. And I think this is kind of just another type of variation, sort of akin to sequence variation. And while a lot of these sequences, these combinations of chirality are not going to be functional, occasionally you're going to, just by mere chance, have some that are aligning. And the fact that the homochiral molecules tend to produce more of the same of themselves. Once you get a few, you're going to start having more and more of them. And so while it is unlikely, if we're taking the currently known age of the Earth and we're seeing millions of these interactions happening every minute for billions of years, then the low probability of this happening is just basically a statistical inevitability.
We obviously will disagree on that. I will point out that the adenine, that has only a half-life on the order of a year. The cytosine has a half-life of 19 days. It's not reasonable to expect that once even the basic building blocks have been made, much less have they been made according to the right chirality, that it's just going to lay around. The other problems that I haven't gone into, those are the other paradoxes, is that if we have this in a solution of water, these molecules don't connect, because that's what they call the water paradox. You can't start life with water, and you can't live life without water, and that's the problem. Is the molecules don't connect because we need a condensation reaction, the equivalent of a condensation reaction, to happen in water. The tendency is for a hydrolysis reaction to happen in water, and so these molecules don't even connect. So even if we had the Earth full with these oceans, it's just not going to connect. And the other thing is, there's no reason to think that just because you have some homochiral concentration that it's going to start generating homochirality spontaneously. We have that in evidence when we kill a cell. If you take a cell and you poke a hole in it and you let it die, it doesn't keep pumping out homochiral molecules. It ends up dying, and all the amino acids will eventually racemize, and the DNA has a half-life. It's going to break apart. So we actually have observational evidence that even if you start out with something very promising, it doesn't spontaneously start creating homochirality, homo-linkages, as I've described here. It spontaneously falls apart. And that's the asphalt paradox that Benner was talking about. It is the general tendency, using structure theory of chemistry and some of the space of small molecules, that the overwhelming tendency is, if we start out with these biomolecules left to themselves, not in any organization, that it's going to head toward asphalt. And that's what I've tried to demonstrate here is what is the asphalt aspects of the asphalt paradox. I know I threw a lot of technical stuff at the listeners, but this is kind of the level of detail that's needed to kind of resolve this. And I hope some of those who are maybe on my side of the discussion will actually pay we'll be interested in reading books like Dr. Tan and Dr. Stadler. It's great to actually understand it. And one other thing is, I hope I've given a different approach than information theory, and also at least an approach using the law of large numbers and structural biology with the origin of life. So whether people agree with me or not, I hope at least they've gotten a perspective and maybe a little bit more appreciation for all the work done by researchers, even those who are not creationists, on the study of origin of life, because this is obviously hard work and a lot of study to get this far to understand these questions.
And if you had anything to respond with there, Snake, go ahead.
Yeah, I mean, I would also just add that there are lots of known ways that nucleobases can synthesize in ice, and ice also extends their half-life as well. And they've done experiments where they actually evolved ribozyme activity where it was able to polymerize other RNA in ice. Not sure what the chirality situation with that is, but yeah, I mean, it's just really adding another layer of sequence complexity, but we've seen that basically functional sequences can come out of basically randomization, and much more complex levels of sequence structure can produce levels of functionality than just the chirality problem. So I think that's less of a problem than actually getting the nucleobases in a functional sequence. But was there anything else on this topic?
I mean, I had some more slides, but if you want to say that for another day.
Yeah, it's up to you if you wanted to go through another few slides, or if you wanted to go more into the evolution aspect. I know Sal mentioned earlier at the start of the debate that what we primarily see is devolution, not evolution. I don't know if you want to touch on that, Snake, and kind of go a bit of a back and forth there. I do still have some time on the timer, about 20 to 30 minutes left. So however you guys want to proceed dialogue-wise, I'm all for it. We're pretty easy going.
I actually just have a few more slides. And it will cover a little bit of some of my, it's a privilege to cover a little bit more of some of my other work. And okay, so, and I really want to thank my counterpart here, Snake. I appreciate the conversation, and I'm glad that you can represent some of the views that are out there too. By the way, I want to say I'm a firm believer in letting both sides of the argument at least have the chance to engage each other in the same venue. I think that's really important. So
yeah, and I'm here to learn what your guys what your problems with the model is too.
So let me sorry if I'm fumbling here. I'm kind of learning how to do all of the screen sharing. All right, so this is change Tan's code. Okay, good, it's up, and I can, let me see my, thank you for your forbearance, everyone. So I'm just going to go through some slides. So I should point out that there are infinite ways to make keys. It doesn't make matching lock and key sets highly probable from random cutting of metal. So the issue isn't that we're aiming for a specific single target. What we're kind of like the more design target, this is a structural argument. Just because there are an infinite number of ways to make a matching lock and key. So like if you took a random key here, there's really one, there's only a finite set of, there are only a limited set of locks that key can open, or vice versa. So even though there might be an infinite number of combinations that we can make between keys and locks, it doesn't make kind of the random cutting of metal highly probable. So even if there are multiple targets, so to speak, it doesn't imply that it's that something is probable. Same with airplanes. So there are infinite numbers of ways that we can make airplanes or spaceships. It doesn't mean that we can assemble one from a junkyard in a tornado. Now, one thing I'll point out for the creationists out there, I'm actually suggesting that defining life is a red herring. So the issue isn't how to define life. The issue is whether we can find a simple self. The issue isn't also whether we can find a simple self-replicator. The issue is whether the structures and functions of life are improbable, just like the house of cards. And I actually suggest, and this is kind of heretical, I would actually say we should de-emphasize information theory arguments. Information theory arguments can be framed as a subset of structural and functional arguments. So I recommend using structural and functional arguments, not information theory arguments. That's just my preference. And I just a little commercial. I didn't mean to use commercial break here because that's a certain code word for me to take care of my mom. But anyway, I'd like to also highlight a book where I got some of my ideas today. It's by my friend Walter James Remine. He wrote The Biotic Message. And I would say that life is constructed to look in a way that doesn't look natural. So if you remember that college exercise I gave, where I gave the students coins and dice and say, try to make it look designed. That's what Walter Remine argues. It looks designed. The structure looks designed, but it is also kind of the structure that you wouldn't know unless you looked. So this is one of my favorite proverbs. It's the glory of God to conceal a thing. It is the glory of kings to search out a thing. That was a theological deviation from my main talk. So that's just something to think of. I already covered that. I'll point out, argument by contradiction is not argument from incredulity. So I'll give some examples. If I said, oh, gee, I don't know how 500 fair coins heads can be the product of chance, that's framing it as an argument from incredulity. But if I said 500 fair coins heads is not the product of chance because such a configuration by random processes contradicts the law of large numbers, that is an argument by contradiction. Or if I said, I don't know how a tornado can make 747 jetliners from junkyard parts, that's sounding like an argument from incredulity. It's more forceful to say tornadoes don't make 747 jetliners from junkyard parts because random connections don't make specific connections. That's an argument by contradiction. And I'll tell you, I'm sorry I have to say this, but Nick Matsky and he was an evolutionary biologist. He's now gotten his doctorate. He was involved in the infamous Stover versus Kitzmiller trial, helping the legal team of the pro-evolution side. We asked him a simple statistics question about what if he came across a table that had all the coins, all heads, 500 coins, all heads. Would he think that's the product of random chance? You could see that he didn't answer the question because it made him uncomfortable because he knew we were starting to formulate better arguments using the law of large numbers, which I presented here. This molecule on the right is a molecule that I work with my colleague Joe DeWeese. It is the topoisomerase type 2 molecule. In that this is a little bit of structural biology where you can actually see what the protein complex looks like. These are actually two of the same. The red molecule is sequence-wise identical to the blue molecule. And when they pair together, they form the topoisomerase complex. You'd be dead without it. That is an example of the way this thing works is an example of a Rube Goldberg machine. The way it works in life with the other chemicals. And I'll point out life has been described by various biochemists and even in some textbooks and even by a Nobel Prize winner Z Sankar. It has a lot of Rube Goldberg complexes, a lot of Rube Goldberg complexity. So this one I think is like a goodness. This is a stapler. So when the alarm clock goes off, it goes through some things, and this scissors cuts the string, and then the shoe falls on the stapler. It's a Rube Goldberg machine. This is just a conceptual one. We have other ones like this. I'll show you the God. This is now kind of my personal opinion. This is a God-made Rube Goldberg machine. You see all the connections there? I'm going to just zoom in. You can see all the interactions. This is what is needed to be able to make the molecules of life. This is a metabolic diagram. So to be able to orient those molecules and overcome the law of large numbers, this is the system in life that builds those molecules the right way and helps it connect. So that's all I had for today.
All right. So I got a couple things written down in my notes. So I think I actually appreciate you talking about the argument from contradiction, and that's more sophisticated than most. I think the argument from incredulity comes from where we see arguments from analogies, and the analogy is inappropriate somehow. And that would be kind of showing that the argument isn't well represented by the analogy. And so I think it's more accurate to say it's kind of an argument from incredulity, because we're not, if unless we're representing the problem accurately, and eventually with any analogy it's going to fail. And basically we're not actually talking about the problem at hand, and we're talking about something else, and so we're actually not addressing a true contradiction. Did you have any comments about that?
No, I appreciate the feedback. I think as far as what I talked about today, I think the disagreement can boil down to the applicability of the law of large numbers to the molecular structures. And I'd say that's fair for people to disagree about that. At a very personal level, it just looks, I mean, this is not a scientific comment, what I'm about to say. It's just too hard for me to believe. I used to believe in abiogenesis. I thought it was really cool, and I used to believe in evolutionary theory. I used to think that was really cool, that things will just keep improving. There's a certain appeal to that personally. The idea that simple things can just spontaneously become better, and that the human race will keep getting better and improving forever, and the universe will just be a better and better place each day. I know that that's a real extrapolation, but I was just a teenager. I didn't know very much then, but that's how I viewed evolutionary theory. I had, it was something that I accepted, but then, as I began to look at these considerations, some of which I presented today, it just became too hard to believe. So maybe you could say that's incredulity there, but some of that incredulity is built by just what I see arguments by contradiction of what we should expect from chemical interactions.
Well, it is kind of a fine line, yeah. And but the one thing that kind of comes to mind, the reason I kind of err on the side of abiogenesis is it's not necessarily that I believe it. It's just more like this is what we have the most information on currently. It's the most plausible to me. I think it's indisputable that certain systems, when they're already there, that life can get more complex, that evolution will occur. But I think it is a pretty interesting topic to explore of, well, does that mean that complex life can come from, like, just chemicals in the water and things like that. But really, what kind of stops me from going down too much that rabbit hole is, well, actually, I guess I go all the way down the rabbit hole to maybe a creator, like well, we can think about aliens, but then, you know, they would have to have some sort of biology that is able to come abiotically, or whatever they're made out of would have to come from inanimate objects. But going down or going up all the way to a creator God, what stops me is kind of like when I try to conceptualize it, obviously it's claimed to be more complex than human minds can handle, but it seems to me that a God itself would have to be made from simpler parts. A God would have to follow the rules of logic. It can't itself contradict. Oftentimes it's said God can't contradict himself, and so, but a mind can hold two different thoughts at once, but we're talking about a perfect mind. But so the way that I kind of conceptualize it is, if God is this thing, either it's a perfect being that can't like have that can't contradict his own thoughts, or can't hold two different thoughts at once, or two contradictory thoughts at once, or he kind of has some sort of substance. He behaves by some sort of rules. So I understand this as he's made of something, or something is allowing him to come together and emerge from him. So at some point, I don't actually, if any of that makes sense, at some point, it seems that eventually something has to come, not necessarily from nothing, but from simpler parts. Even the creator has to somehow have gotten here from something that is less complex than itself, or is made of something less complex than itself, and would therefore have to form. And the other part of that is, if we're going to say that all these things that are so complex has to have come from some sort of intelligence or creator, that creates an infinite regress problem. So the only way in my mind to solve that is that simple things can create more complex things. And that's not the rule of the universe. It's just one of the options. Otherwise, if complex things can only come from more complex things, that creates an unsolvable problem in my mind.
I do have one question. This is not a criticism, and again, this is an opinion. I'm not gonna say it's whatever you answer. I'm not gonna pounce on it. I just wanted to promise that. Just first off, I can empathize with almost anyone that's not seen a miracle personally in their life, that they would think everything happens by natural processes. So that said, and you don't have to answer. You could say, I don't know. I pose this question: is if you'd seen a miracle live with your own eyes, would that persuade you of? I mean, can you imagine some miracle would be great enough that would make you believe in God, if you saw it, directly?
It would definitely make me lean that way, or start down the rabbit hole. It's without an example, it's hard to say.
Sure.
Because I could see a miracle and then conclude that maybe ghosts are real, and maybe that could lead down a separate rabbit hole. Like,
Right.
Okay, so souls exist. Okay, so what else?
Right.
And
I'll tell you where I
would need a pretty big miracle or series of miracles.
Sure. Okay.
Maybe you could give an example, or
Well,
But yeah.
maybe I could just tell you where I was actually leading with that. Because what I try to say is, hypothetically, if the origin of life were a miracle, let's just say hypothetically it were a miracle, that would mean that the mechanism couldn't ever be repeated in the laboratory, because by definition, the origin of life in my scenario was a miracle. So then we wouldn't actually be able to elucidate the mechanism. We might go on forever trying to solve the origin of life using natural means, but we'll never actually figure it out. So this leads to what I call a dilemma, because if the origin of life were a miracle, if someone's insistent that, I mean, personally or whatever, and again, I'm not trying to be too judgmental, if they have adopted a policy that they're only going to search for natural explanations, they're going to go on forever and not be able to prove the natural route. So then the alternative for someone who will accept miracles, at what point, how many naturalistic experiments or theories studied, what will be their threshold that they decide the origin of life is a miracle, even though they may personally have never experienced the miracle in their life? At what point will they consider it a miracle? And I don't think that there is I don't think there's a formal way of deciding that answer. Each person will maybe make that call at their own personal level of belief. And I'm just saying that for me personally, it's too hard for me. Like I showed that metabolic diagram. It's just too hard for me to believe something that complex could assemble, because I don't think the steps are sustainable. Because if it's halfway built, it's going to die. It's just like that cell that got poked. It's going to be a dead thing, a quote unquote asphalt at some point. So I'm just throwing it out there. I'm just saying that if the origin of life were a miracle, no amount of naturalistic research is going to find that. And also, there's no new research program that's ever going to persuade someone who's adopted that viewpoint.
Yeah, I mean, the complexity of the algorithm is basically built slowly. It doesn't all come together at once, and then each level of complexity that you add, it kind of usually will become dependent on that. So that's a little less convincing to me. And I do get what you're saying about the supernatural. Each person might need something different to convince them. The problem with that is that it can't really be studied scientifically, and you can't really say it's science. And I have no problem with truths being inaccessible to science, but it's just that, if it's not scientific, it's not scientific. And so far, science is basically the only basically reliable way to study anything so far. And for example, like maybe God used knowable or known chemistry to assemble cells, but his knowledge of how it works, or the ability to track what he's doing without losing focus, like his processing power, may be something that's inaccessible to us. And that would kind of synthesize the two kind of different perspectives on this, where you could have a biogenesis and a creator at the same time. You could have both. But the problem is, well, you said something about what kind of evidence would convince someone of the supernatural, and I think that the probability and plausibility of that would go up dramatically if we had any examples of that. Like, so, for example, we had thousands of years without science, and so scientific explanations were almost useless because no one understood what the process was. But as soon as science started actually producing results and started giving us explanations, not just explanations, but explanations that were able to be extrapolated upon and be able to predict and produce new explanations and new technologies. As soon as we start doing that with supernatural ideas or things, then I'm much more readily able to accept, the next stage or the next supernatural hypothesis. And I haven't experienced a miracle, and I'm actually pretty disappointed because I know a lot of people who even like an alien abduction. I know a lot of people who have alien stories or ghost stories, and I would love to experience one of those because I think it would be a more interesting world if there was some supernatural element. I don't see it.
Oh, I really appreciate you communicating that. I know we're running up on time, and I'd like to thank the moderators for letting me for letting the conversation continue. I have maybe one thing to say before I say goodbye.
Oh yeah, no rush. I'll say one thing. It was very engaging. Everybody enjoyed. The chat's been very lively. You've both been very respectful. We do have some interaction from the chat that can lead to some further discussion before we close her down for the night. But I know you were about to say something there, Salvador. Yeah. So I didn't mean to cut you off, but go ahead.
I had a couple comments left. Sorry to interject.
Please.
You can finish up, but I just have a couple of things left that I wanted to get to before questions.
Oh yeah, of course. I'm not. Yep. You guys take your time.
Well, I'll say that in my personal life, I think I've seen miracles, and people that I've known that got converted to Christianity have maybe not personally experienced them, but had friends that had seen them. So if you wonder why I have a certain inclination, that's part of the explanation. I met astronaut Charles Duke. He was the youngest man to ever walk on the moon. When he came back to Earth, when he went to the moon, he wasn't a Christian. When he came back, his life was a mess. He became an alcoholic, and his wife was suicidal, and his marriage was falling apart. But then they started going to church, and he became a Christian. At one prayer meeting, he prayed for a blind girl, and she got healed. This is the account is in his book, Moonwalker. Since he was a national hero at the time in the 70s, there's really no reason. I know of no one that would say that he made the story up. So if it were just a coincidence that the young girl got healed of blindness right after he prayed for her, if that's a coincidence, that would probably be about the best naturalistic explanation that I could think of. No one questions his character, and he's lived his life as someone, not as a faith healer or some televangelist trying to get so much attention. He's quietly living the rest of his life, ministering to prisoners, the outcasts of society. That was one example of something that moved me very deeply. And perhaps that is why I'm more inclined to accept miracles. So the other side of the coin is, if we could actually work miracles in the lab on demand, then it's not really a miracle. If we could create life on demand or any miracle we wanted, at that point, well, we would be equivalent to God if we could just conjure up any miracle at our own power or the powers of God. I believe that these are difficult questions, why God will reveal himself to some people and not others. In the New Testament, Jesus, after he was resurrected, appeared to 500 people. It certainly would have been easier if he appeared to everyone, and we probably wouldn't be having these debates. But I believe the Bible teaches that God does hide things for his own purposes, and part of that is to kind of humiliate the people who think they're very wise and smart and learned. That's described in 1 Corinthians chapter 1, 26 and on, verse 26 and onward. So for that reason, I really do sympathize with people that when they say they wish they could have seen a miracle and it's never happened. So I totally get that, and I don't fault anyone for being skeptical if they've not personally experienced it. And all I could say is that uh, when someone believes that they've seen a miracle, or they find credible someone's witness, like astronaut Charles Duke, um, that affects how they'll view this question of the origin of life.
Yeah, I do think that there's something almost, if not truly transcendental, about like high order thoughts. Even like, I don't know. I think just the love between someone and their dog is transcendental. Maybe not for the dog, but I think there is something about finding the inner truths that it's very powerful. But I don't need a supernatural to access this. So I mean, I kind of call myself a spiritual atheist along those lines. But I think that that's explainable just by the brain. But as for like miracles, like curing of the blind, I think that I would prefer that to be true, honestly. Kind of, there are questions of, okay, so why did this blind girl get healed but not this blind girl? I would still rather that be a possibility, and I think that's great. But personally, again, I have pretty much the exact opposite experience. I've been at faith healings, and I have loved ones that have done faith healings, and nothing happened. So, I mean, maybe they had the wrong God, who knows? But I think that if it was possible, it would be demonstrable beyond these reasonable doubts. I think that we would be able to study them and be able to pick out and be able to demonstrate causation instead of correlation and things like that. So I think that science is a little bit more powerful than these personal experiences, because they can be objectively verified no matter what your experience is, at least as long as you have the equipment and some of the training. Then you can study this yourself. And then, unless you had some more comments about that, I just wanted to get a couple of other comments out real quick.
Go ahead. Thank you, Snake.
You mentioned something about the matching lock and keys, the improbability with that, and I just wanted to point out in biology that a lot of times, I mean, this is one of the problems with things like infectious diseases or poisons, is they can mimic the proper key that's supposed to, quote unquote, supposed to fit in the cellular receptor or whatever, and it can either randomly adapt to have that same key, or a lot of times, like with poisons, like carbon monoxide will actually fit into the same lock as oxygen and will lock out oxygen. And so I think that that's not quite a demonstration of something that's like a lock and key being a miraculous lock and key. And then with the in line with the Rube Goldberg machines, I think life is often analogized to Rube Goldberg machines because it's so complex, and this leads to this, like, indirectly through a series of basically crazy cascades. But I think Rube Goldberg machines are examples of things that are designed to be more complex than they need to be. And so basically, if we find that kind of pattern in nature, it's either like a cosmic joke, I guess, because actual Rube Goldberg machines are they're funny. They're kind of jokes. Or I think the other possibility is just it's kind of a mess because it's just chemistry. It wasn't planned out, because one of the hallmarks of design is if we're trying to have a serious functional design, then we're going to try and eliminate as much of this unneeded stuff as possible. And so I think when I look at life, I see unnecessary design elements, and a lot, not just the complexity, but kind of the traits that follow like an evolutionary pattern. So at the cellular level, it would be complexity, but at the macro level, it would be things like, well, why do penguins have the bone structure of birds that fly when they don't even need those kind of bones? So when I look at nature, I see not design. It doesn't have the hallmarks of design for me. I guess a lot of this is up to, interpretation or personal experience, but that's kind of why I defer to science, because that process, not that science equals truth, but that science is the most reliable way that we know of testing these interpretations. So that's all I got so far.
Well, thank you for the feedback. Actually, one of the reasons I'm doing this is I've been commissioned to write a book, tentatively titled Stairways to Understanding. And so these discussions are an opportunity for me to improve some of the ideas that'll be represented in the book. So your feedback on the lock and key was it's something I'm going to use to improve what I'm going to say. So I'm indebted to you. Thank you.
Oh, cool. Yeah, I think understanding should be the goal of these discussions for sure.
Okay, well, that was a really respectful back and forth dialogue. Like I said, we all had a lot of fun. I know we're now past the hour and a half mark, and I think, Sal, you said that you had to go anyway?
No.
Okay, because I did have a couple interactions from the chat. Let me, I saved a few questions. One from Bill Morgan that I think can lead to an interesting brief back and forth between you and Snake, because Bill Morgan asked you, Salvador, could you please ask Salvador what got him to reject evolutionary theory and change his perspective?
Wow. Even though I actually rejected it maybe for what would be considered a wrong thing at first. It was the origin of life. So origin of life is not considered part of biological evolution, but that was the beginning. That was definitely the beginning. What I'd say really started to seal it for me was the study of the emergence of eukaryotes, because that's at the base of the tree of life. And that's actually what started to lead to Dr. Tan studying this question of origin of life. She started to reject evolutionary theory because she had to teach molecular cell biology. So when she saw the eukaryotic transition, that really started to do it for her. It did it for me. This is much later. But even before that, I began to have really grave suspicions just because of the complexity of life. And maybe something that wasn't scientific, just kind of the harsh treatment I got from people when I started to ask questions. And then if people look at my history, I was at George Mason. My undergrad was at George Mason, and I knew Dr. Carolyn Crocker. For some of you, she was in the motion picture Expelled. She was in the motion picture Expelled. A reporter from Nature came and visited us when I was having my first ID meeting at George Mason, and Dr. Crocker was there. Our story was released 3 weeks later. She got fired, and I said, this just doesn't smell right. If she's wrong, she's wrong. And I just didn't like seeing that people were. It's like people had an agenda to suppress discussion. So I began to have a lot of suspicions at that point. I thought evolutionary theory was actually, there were a lot of questions up until the last few years. So I've been a creationist a long time, an old Earth creationist for since I was 16 years old. But then I started to have doubts, and I started to at least be on the creationist side, saying that these questions have to be answered. So I thought the evolutionists argued their case extremely well. But I did study a little bit more evolutionary biology in graduate school, and I said, yeah, you can build nested hierarchy trees, but those don't explain the mechanistic issues. So it's been a long process, and I could. So when what was the gentleman's name, Mr. Morgan? He asked what persuaded me.
Yes.
So, I'd say maybe I didn't believe. I probably rejected evolutionary theory for not the best of reasons at first. Okay. I think I have better reasons especially after the last few years, especially after working with Dr. Sanford on the theory of genetic entropy, because he sent me to the NIH to just kind of find out all that's going on. And when I've seen the complexity of chromatin, and I ask evolutionary biologists, well, how did chromatin evolve? And they don't have answers. And so I started to ask, okay, what about other systems like the lentus retractor muscle in the fish that has to be the ciliary muscles in the eye, or the fact that the fish, we evolved from fish, supposedly. Did you know that the anus and the urogenital opening, which is quote unquote like a vagina, they're ordered differently. They're wired backward in the fish relative to humans. So I just see things like that. And I said, well, we can build nested hierarchies, arrange the creatures in groups, but you have all these kind of nasty transitions that don't really seem, they sort of need miracles to make the transition work. So, so maybe to say, I didn't reject evolutionary theory for the best of reasons before, but I think I have better reasons now.
Awesome. I really appreciate that answer there. Snake, and any thoughts on Salvador's answer?
Yeah, I mean, I guess to start kind of off with the fish's anus example, that's a pretty good title for some kind of argument, maybe, the fish's anus. But I would say that nested hierarchies of traits are not always like, we don't still have gills. So you can add and gain traits, but it's basically just the way that they're organized. Like, again, like with unnecessary design elements. So it's I don't know. I mean, I don't want to get too far into evolution, but I guess again, with my example of the penguin, there's no reason it needs to have the bones that it has. That's evidence that it was derived from a flying bird. And maybe the design was derived outside of the process of evolution, like in God's notebook, something like that. But it's clearly derived from a bird. But I think if I were to be persuaded that there was a designer, I'd still believe that this designer... I basically still believe in evolution and probably abiogenesis, in the sense, well, I guess in the sense that like God would have basically put this together in a laboratory using chemistry, and most of the chemistry that we already know about along the lines of abiogenesis. To me, the greater God would have basically designed the universe almost as a Rube Goldberg machine, but something so highly ordered and complex that it could actually automatically create on its own. I think that I would be more impressed with a God that created the universe, and then the universe itself was planned in such a way that abiogenesis could happen. But I also would probably believe in a God that just maybe descended to Earth and put life together in his lab, however that works, and then let it evolve. And so I don't think abiogenesis or evolution actually disproves or refutes a God. These are just kind of topics that display they really highlight the different perspectives on these processes. And then I don't think someone should be fired for expressing these opinions or expressing doubt. In fact, that's kind of what science is for, expressing doubt. Like, as long as you're not teaching the exact opposite of what you're hired to teach, I don't think, if you're just expressing opinions that have nothing to do with your actual job, or even just skepticism of what you're hired to teach, as long as you're teaching it, as long as you're doing your job, I don't think it should be fired. And I would kind of compare that to getting a little bit heated here, but I would kind of compare it to damning someone to hell for just being wrong about the God question. If you're just wrong about some scientific question, I think we should have the freedom to be able to be wrong, to kind of go out there and test new ideas. And that's kind of the point of science, is, throw ideas at the wall, see what sticks.
Awesome. Thanks for that response there, Snake. And any thoughts on any of Snake's points there, Salvador?
I just wanted to say one thing in this. Sorry, the plug for my upcoming booklet. I actually think the patterns that we have creatures that go from simple to complex. I actually think that that's a design feature. That is a stairway to understanding. The reason we have chimps that are similar to us, and then other creatures that are not so similar, like bacteria, we can actually arrange them in a sequence, going from bacteria to eukaryotes to like a multicellular creature, like I don't know, just pick like a sponge, going all the way up to a fish, to a mammal, to a primate, to a human. That looks like an evolutionary sequence, and I think creationists sometimes de-emphasize that, but I think that's a real feature of biology. And I'm arguing that that's not a physical common descent. That is a conceptual ladder. It's a conceptual stairway, so that humans can understand we're fearfully and wonderfully made. So I'm actually going to say, and actually agree to some extent with my colleagues who are evolutionists, that there is a sequence going from bacteria all the way to humans. We could go take the stairway all the way to the molecules of life, from molecules to man. There is a sequence from simple to complex, but I argue that each of the steps taking up that stairway is just, it doesn't, if we see a stairway, we know it's designed. It's improbable for these transitions to happen. So that's probably why it was, when I said I rejected evolutionary theory for not the best of reasons. I was told there were no transitionals, and I found out later that we could actually argue that they're, at least conceptually, you could say that they're there. So, back to Mr. Morgan's question, I'd say that if you asked me this 40 years ago, I'd probably not give you the right answers. So, thank you. That's all I had.
No problem. Over to you, Snake, if there's anything else you wanted to kind of address regarding that. I think the audience is enjoying this specific back and forth. So if there's anything else you wanted to address, go ahead.
No, yeah, I think that's really interesting. I respect that. The sense, I think it's undeniable that most life forms are derived from some other life form. And I think it's important to recognize that even in design, where even if penguins were separately designed from other birds, it's clear that maybe that God, whatever his notepad is, wherever he stores his designs, he took a bird and morphed it a little bit. And whether that's possible as a natural process, or whether God did the morphing. I think it's really important not to miss these derived designs.
Thoroughly agree. Thoroughly agree.
Cool.
Thoroughly agree.
Awesome.
I know you had a question there, Salvador, regarding chromatin. I was wondering.
Oh, that was more of a rhetorical question. If anyone's actually seen chromatin remodeling and all the proteins involved in chromatin remodeling, it's pretty amazing, especially the chromatin in eukaryotes. So that was more of a rhetorical question.
Oh, no problem. Is that something you'd want to respond to, Snake, or?
Well, I mean, I do think it's pretty amazing. That's why I study biology. But I just think that I've seen examples of these things getting ordered and more complex on their own. So I think that using at least methodological naturalism is the best place to start. But I don't have much else beyond that.
Okay, awesome. Yeah, I think this has been a lot of fun. Like I said, we've all enjoyed. If you guys both wanted to say some final words, I guess, before we call it a night here, I'll say a couple hours really flew by. You both, brought up a lot of good points, and it's been a very enjoyable discussion. So thanks for doing it, Snake, and thanks for doing it, Salvador. So I'll hand it over to you guys if you wanted to say some closing words.
I think my closing words is, I am a Christian, and I believe that abiogenesis, the problems are evidence for creation and for the Christian God. I mean, you couldn't derive the Christian God simply from the problems with abiogenesis, but it contributes to my belief in creator and intelligent design, and through a process of kind of a miracle, like Jesus converting water into wine or making the loaves of bread. But apart from that, the main thing I wanted to convey today is the paradoxes that Steve Benner put out. So if one wanted a purely secular perspective on the origin of life, at least the perspective that is sympathetic to mine, it would be Steve Benner's work, where he describes the paradoxes like the asphalt paradox and the water paradox and the information need paradox and the single biopolymer paradox. These would be great things to study. Unlike some creationists, I actually hold the abiogenesis researchers in the highest esteem. They've done really great work. People like Steve Benner, they've actually made me believe in special creation. And I would hope creationists would support the scientific enterprise. It's not always in our favor. As I said, I had friends that were fired and persecuted by the scientific enterprise, but I don't want that. I'm hoping that people will look beyond that and not be afraid to try to study science. And I think studying a little chemistry and cellular biology is great for everyone, whatever their views on creation evolution. I think it's just great if people will learn more science. So that's all I had.
Awesome. I really appreciate that, Salvador. Over to you there, Snake.
Yeah, I really enjoyed this discussion, and thanks to Salvador for coming on. And I would just say that from my perspective, I think it looks like we have most of the puzzle of abiogenesis assembled. Currently, we know the probability of naturally forming monomers, nucleotides, lipids, amino acids, sugars, and a lot of other complex organic compounds. That is a probability of 1, basically, meaning it will happen. And we have a lot of evidence. We see that this will happen naturally. It happens in a lab. We have meteorites with a lot of these compounds in them. So unless God's sending down meteorites with half-formed organic mixtures, it seems that it's a very natural phenomenon. And there are a lot of holes in the puzzle, but I think the general picture of the puzzle is showing that the probability is pretty high, especially over a long period of time. And I would like to do some research on the points that were brought up tonight, and I'll probably have some to shoot back. But you've given me a lot to think about, so.
Awesome. I appreciated that closing statement there, Snake. Any final words or questions from either the co-moderator, John, or the producer, Praise?
All right. I can refuse, I guess. So ask. They know me, but I don't think I have that much credibility with them. Even with my own boss, because he's so reclusive. He's a swell guy. It'd be it'd be hard to get John Sanford. I might be able to get. I probably could get a few minutes with Dr. Tan, or maybe even Dr. Stadler, who wrote this book. Maybe with Dr. Joe DeWeese, who's a young Earth creationist, but he's an associate professor of biochemistry and also a adjunct professor at Vanderbilt University. So he's very, very smart. So some people like that.
Sal, I would actually.
I'm curious. How did you meet or get associated with John Sanford?
I went to the. I showed a picture of Walter Remine, and it was through Walter Remine I met John Sanford at the International Conference of Creationism, which is Young Earth Creationism, 2008, and we got introduced. At the time, I just left the aerospace industry as an engineer, and so I was getting involved in creationism. And then in 2014, Dr. Sanford hired me to be his part-time research assistant. I've since become a full-time research assistant. And I was very impressed with everything that both his attitude and especially the fact that he'd been an atheist and then eventually became a creationist. I found that story compelling, especially his accomplishments as a scientist. So a lot of it was I sought him out, and he's just a very gracious and kind man. And so I've been working with him now for 6 years. And so that's how I met him.
Met at a conference. Go figure.
Awesome. Well, thanks for that answer there, Salvador. John, I think you had something to say.
Well, two things. One, so the gentleman you mentioned at Vanderbilt, I actually live in Nashville, so that'd be interesting. I'd love to get connected with him since we must live not that far apart from each other. The one of the other things I find very interesting and I'd love to get your opinion on is, as you're talking about the structural aspects as a engineer, is part of what makes the designer requirement so adamant, is when you're looking at the structure, are you seeing the equivalent of, I'm just analogy standpoint, are you seeing the equivalent of gears and parts and everything in the chemical structures rather than just pure cause and effect?
Gears and parts, it'd be more like interconnecting parts. The parts have to be very well shaped to interact with each other. Now, notwithstanding what Snake said, there are fittings that are simple enough that it can be random chance can actually resolve it. So I'm not disputing that, but there are some connections that are rather precise, both in size and shape. I showed the molecule, the topoisomerase molecule. That one has to be pretty much the right shape and size and have all of the electrical properties, where you're exposing the positive and negative kind of charges in the right direction to be able to do what it does. And so that's a whole nother conversation. I kind of alluded to kind of the basic structure today, where you just have to get things to even line up like a railway. So like if you just even get the Scrabble letters to be in a line so you can read them, that's a very simple aspect of structure. That's at the abiogenesis level. At the level of functioning proteins within membranes, or proteins connecting to each other, I could show you some mind-blowing complexes where we have probably 10,000 molecules connecting together in an orchestrated manner. Just to me, that's what you said with the gears. It's like, well, yeah, that's kind of in the right direction, but when you actually see all the parts, it's like a car being put together. So many things having to connect just right.
Well, that's part of where I was going with that. I assumed that's kind of where your mind went as you observed all these different things. Of, wait a minute, the gears analogy doesn't even come close to expounding upon all the different pieces of the puzzle that all have to fit together. Is it fair to say that in these structures that you're talking about, the levels of improbability go even higher than just what we were talking about in the context of abiogenesis?
It's hard to say. The ones in because actually some of those structures have to be solved to make abiogenesis possible. Like the helicase one, I showed a picture of the helicase. So that's part of the probability. And I actually haven't worked through the numbers because they're a little harder. It's easy to use is an I don't know a good answer. That's probably the best answer I could give. Because
no, I actually find that very interesting. So if I understand you correctly, you are saying that to dumb it down, are you basically saying that those additional components are fundamental to the proverbial chicken and egg problem for abiogenesis?
Some of those, and we can probably boil it down to, at a bare minimum, of maybe 415 proteins. That's just the proteins. We're not even talking about the class of carbohydrates. There are a lot of other things like that have to be in what they call the cellular cytoplasm. But there was something I wanted to say about structure. Oh, before I forget, John, the reason I'm using structure arguments now is that there wasn't even, the field of structural biology sort of had its beginnings way back, but it's only like in the recent years that I'm even seeing people use the word structural biology. That's because we didn't quite have the level of instrumentation that we have today to actually start to estimate what molecules actually look like to the level that we're doing it now. Like that topoisomerase is a great example. They had to use a technique known as X-ray crystallography to derive that, and they're doing it more and they're doing it better. And we also have computational models. So what's happened now is, it used to be like maybe just for rough figure, maybe 20 years ago, we used information arguments and mutations. But now that we have structural biology, you can actually kind of guess what happened, what a mutation does. It breaks the components down. And there are machines like the ATP synthase. If you've ever seen the flagellum, the ATP synthase also looks like a little motor. And when you start to change the spelling, which are mutations, that shape changes. And you can at least now conceptualize why a mutation is damaging. That's why I like the structural argument. You can actually kind of envision that component no longer fits the gears and fits very well anymore.
So are you saying that the things like point mutation in the gene sequence, for example, is going to potentially devastatingly alter the specific structure that's required? for
That's
the end
correct.
function.
That's correct. Now, I'm going to give a little caveat, and this is something that I'm going to advise creationists. I would not. Proteins can be mutated to some degree. They can tolerate, depending on the protein,
Right.
it can tolerate a lot of change. But there comes a point when it's too much. So I'm going to give you a rough figure. They're probably 12%. If you have a protein of 1,000 amino acids, 12% of them are probably going to be really critical. So you might be able to get away with mutating a lot of in between, but there is still a lot that you cannot. And that's the proper way to calculate the probabilities. That's not to say that when you change something and it doesn't immediately fail, it's like saying, well, your tire can lose a little bit of tread and your car still goes. At some point, if you keep pulling off enough, it's just not going to work.
So would this be what you're talking about now? Would that support the premise of genetic decay of, hey, yes, it can still function, and yes, we can still be alive, obviously, but to your point, we're losing air in the tires, and the efficiency and the overall top level functionality that could have been is no longer available because of the generation of the genetics in genetics. I mean,
that's absolutely correct. It's again just like the wear and tear on a tire. The car, could even be a race car. The race car driver may not even notice it after like the first couple miles. In fact, when the tire gets warmed up, it might even perform better briefly, but over time it's gonna catch up. And this is why I'm interested in the junk DNA argument, because one evolutionary biologist, Dan Grauer, kind of laid down the gauntlet. He said, if ENCODE is right, evolution's wrong. And it goes to your point, because the ENCODE, the NIH ENCODE consortium estimated that most of the DNA is functional. And that's the other thing. It's not totally information in the digital sense. It's information in the structural sense. It stores a lot of information, or it represents a lot of information in its 3D conformation. So not only do proteins fold, DNA folds into what they call higher order chromatin structures. And that's an intense field of study because trying to cure cancer. So the structural biology revolution is really kicking in. And so point mutations can degrade that structure, both in the DNA itself, which is important for its 3D folding, and also in the proteins that they code for. And not to mention, it will probably also degrade the folding of the RNAs that they code for. A lot of DNAs code for RNAs that have some sort of function that we haven't totally elucidated, and it'll degrade those too. So there's just 3 levels of degrade. You flip one mutation, it'll affect the DNA, it's going to affect the RNA, it's going to affect the protein.
So that's very interesting to
yeah, it's pretty mind-blowing, isn't it?
to hear to expand on that for just a second. One of the things that I know Standing and myself and other folks, I'm sure you have as well, have run into is this very adamant argument that no, there is no decay happening. That's just, creationist fantasy. In academia, in your experience, is that still the standard dogma, or is that starting to be, what is the general stance inside of academia? Do people agree that there is degeneration occurring, or are they still holding to the fact that no, that's just not real?
Okay, for humans, so we have to separate out organisms. It's hard to argue it for bacteria, and I don't argue for that. I don't even argue it for mice. There's, we don't know if rats. There'll be a lot of back and forth on rats. There's almost no question among any major geneticist about human. I mean, you could just, this would be an interesting survey for all your evolution friends that are part of your channel. and their friends, just ask them, do you think the human genome is improving? It'd be interesting to find out. My personal experience is I've never met an evolutionist that says the human genome is improving. Everyone's saying it's deteriorating. They'll cite different reasons, like say modern medicine, so that kids that have juvenile diabetes don't die anymore. But it still is not. There's that uncomfortable feeling that maybe we're missing something, that maybe we were degenerating all along, because we've had kind of archaeological / paleontological findings of human bones from a few thousand years ago. The cranial capacity was a lot larger, so that may suggest they were a lot smarter. And most geneticists will say, yeah, they probably were a lot smarter than we are today. Some people today have photographic memory. I think that was probably more commonplace, and we probably lost that ability. The bone structure looked, the density, it looked very strong. So the average person was probably an equivalent of an elite CrossFit athlete today. And probably the most important thing is, if someone's undecided, we may be in a position to know, because we're sequenced. When I was at the NIH at the ENCODE conference in 2015, they're talking about sequencing 20 million people in the United States, because they're trying to figure out how diseases work. So if we go through that process, we'll have sequences for the grandmother, the great-grandmother, the grandmother, the mother, and the daughter, etc., over several generations. We will be able to see whether we are deteriorating genetically, and whether it can be attributed solely to the environment, or whether it is an inherent tendency in the human genome. So to answer your question, I'd say the sentiment for humans is definitely that we're deteriorating. People will argue about other creatures, and I actually sent Dr. Sanford a very interesting article that the grapes have lost, some of these domesticated grapes have lost 15% of their genes, which is shocking. Their homologous genes, 15% are gone. And even I said, John, do you think that's entropy? He said, that's worse than I thought. So there's some interesting questions. These are relevant to people involved in ecology and conservation. So these are questions of interest to everyone in other disciplines. So
quick interjection here. So something that you've been talking about this on the the grape example, 15% loss of the genes, and I'm assuming that's been in a relatively short period of time. Is that correct?
I don't know that anyone knows the answer. This came out in a paper in Nature that my professor at the NIH just sent me and said, this is kind of interesting. I'm just like, I didn't know that. And I sent it to Dr. Sanford. He said, I didn't know that either. So we're having all these things that we don't know how to explain, and we have some of these open questions. So I'm sorry I don't have an answer for you.
No. The reason I was bringing that up is it just kind of popped in my head of the there's the standard argument of the Neanderthal having 5% more. I think it's 5% more DNA than modern humans. And where my mind was going with that is, well, if the point you were making about potentially superior bone structure, cranial capacity, intelligence, et cetera, were in the past versus now, one, that would completely destroy the entire premise of improvement. That's clear entropy. But that might also explain the larger DNA structure itself of what was lost, or was there anything lost in that? And standing, is it 5%? I know we hear this all the time. I'm having a brain freeze on that piece, but anyway, you follow my thought process there of perhaps this?
Yes, I'm probably just a tad more circumspect than some of my creationist colleagues. I'll say that obviously I'm a creationist, but I'm, before I say something proves genetic entropy, I have to be pretty sure myself. but I'm comfortable saying human genetic entropy seems to be very well indicated. And on a theological note, I think that supports the idea that humans used to have the long ages as attested to in the Bible. We can probably interpret that literally. So that's again a personal view. That's not a scientific view. Can we use genetic entropy in humans to extrapolate it to like bacteria and mice? I'm personally not comfortable with that. Dr. Sanford and others would probably be a little bit more bold, but you know, my job is to kind of be the guy that's a little bit more conservative, because when I pass things on to him, I have to make sure it's not going to embarrass him in any way. So I tend to err on the more conservative side. So I wouldn't say it destroys all of evolutionary theory, but I would say for those who are interested in the genealogy of Jesus Christ, I think that's the human deterioration supports the genealogy of Jesus Christ.
Interesting. That is that's very interesting. And I know I don't want to keep us going forever here. The one of
we can meet again. We're having a lot of fun.
No, I'm enjoying myself. I don't want to bore the honest and be running my mouth here too much. I've been reading quite a few of the recent publications in Nature about the non-coding regions, i.e. junk. I'm sure you have as well. To me, I've noticed a rather stark change in the tone that's being taken by a lot of the authors of these papers. A lot of them seem to be taking the "why have we been ignoring this for so long" perspective. Have you noticed any of that in your interactions and your observations of like, wait a minute, why have we not been focused on this stuff? Because clearly it does have function, not just from the ENCODE standpoint, but hey, we're figuring out this is like directly responsible for all sorts of disease.
It depends on the groups that you're involved in. If you're with the in the departments of evolutionary biology, they've always seemed to be behind. Whereas if you're with the cancer researchers, they've always suspected it. There was a very interesting study that Francis Collins was involved in. His name is on the paper. 90% of the heritable, around 90% of the heritable diseases are associated with non-coding DNA. It was a study that was done a long time ago. That has been, when I was at the ENCODE 2015 meeting, there wasn't any, the overwhelming sentiment was that there's not junk DNA, because each researcher will say, hey, I'm studying this disease. By the way, it seems all of our genome-wide association studies indicate that it's in the non-coding regions it's associated with. So that's in general, junk DNA, it's not been a surprise to the medical researchers. There may be certain aspects, like the higher order chromatin structure, that's been a little bit of a surprise because especially the link RNAs, that takes a lot of research to find, and sometimes we've stumbled on it, and sometimes we didn't have the instrumentation to see it, and we still don't have the adequate instrumentation. But there's been a sentiment change, and I'll tell you, since I was talking about the NIH a lot, John Sanford, who's a Young Earth Creationist, he got invited to the NIH. That was an official invitation, and it was paid by the government, despite what you might hear on the some of the internet sites that said we rented or that Dr. Sanford paid to appear. That is not true. That shows a change in sentiment, that someone with his viewpoint would be invited to talk about genetic deterioration. So there's a sentiment change there. So as far as being surprised, I guess it depends on who you're talking to.
Right. Yeah. It's part of the reason I'm bringing a lot of this stuff up is, and I'm sure you run into this all the time, but in the YouTube universe, a lot of the opposition and the arguments that are made against God or against creation in general seem to be dependent upon the all of this wasteful lack of design. It would be more simple if a designer had actually done it, it would be more simplistic. And the more I learn, the more to me it seems, number one, we don't actually understand how it works. So how can we determine whether or not it's the most efficient way to execute the functions? And then beyond that, the how does one possibly determine what would be the most efficient model? Does that make sense? And
Yes, and I think we're probably approaching the questions in the wrong way. I actually think that there's a lot of extravagance in designs that don't need to be that good, but they are. It's just we talk about luxury and extravagance. There's a lot of that in biology, and Paul Nelson had to say that. There is something to say about the difference between intelligent design and creationism. There are various ways we could frame it. Creationism may have a timeline and specific events, especially the Young Earth Creationists. But the way I like to frame it is intelligent design says things are designed. Creationism says that things are intelligently designed, but the world is also cursed. So there is some waste, and we don't know how to identify it. I wanted to, can I share one screen? Would that be okay with you all?
of course.
I want to show you, this is some work I did on the topoisomerase enzyme. And I want you to look at how different, this is a different perspective on the protein. Do you see here where it says, the C variable term domain? Yeah, you can see my name here. And Joe DeWeese, he's the guy in Nashville. So maybe we can have him on and you guys can hang out. This is something that was published in the FACID journal or something. And this is the diagram I made. I made this, and this is the human. I'm sorry if the font is a little, let me expand this a little bit. I'm trying to make it. Does this look like a computer punch card? Okay, so this is like, the first line is the human topoisomerase, and I'm comparing it with other creatures. But each of these arrows is a chemical modification that can happen on that single amino acid. Call that a post-translational modification. So this is like flipping a bit. So most people think a protein is kind of a static structure. It's actually like a piece of random access memory simultaneously. So it does a function, it does its thing, but it also stores memory. So each of these positions where you see an arrow, that's where it can change. It can flip the bit on or off, and it can be read, written, and erased. In fact, in chemical literature, we call that readers, writers, and erasers. And if you go through the topoisomerase enzyme, you'll see like 1/3 of the enzyme is just all this bit flipping going on. And you can imagine all they're specialized machines that do the reading, writing, and erasing. So like in a disk drive, you have only one read-write head. In biology, you have multiple read-write heads that are just floating around, flipping the bits. So
if I'm understanding what you're saying there correctly, I'm dumbing this down a little bit. You are telling us that this enzyme has the ability to have dynamic computation.
Absolutely. John Sanford saw this. He said, I want you on this 100%. It's like, well, I'm 100% on the other projects too. But he really loved this diagram that I put together, and so did Joe. That's why it was featured in the poster session. But by the way, this is common knowledge at the NIH. But when I share it with people outside the NIH, they're like, wow, I didn't know that.
So in regards to the dynamic computation aspect, the human technology, we're working on it, but the majority of our attempts at dynamic systems fail miserably. Is that a fair assumption?
Compared to life, yes. And I will give I'll leave that up for just a little longer, but when you're asking about the degrading of individual amino acids, you can see why for the human specific, there are areas in the human, you can't just flip this protein off, or you can't flip that protein that amino acid to a different one, it's going to cause that bit to fail. I mean, at some point, just like it's going to degrade the function of the topoisomerase. And when I said that there's a stairway to life, I'll tell you what's really interesting. You can take this human topoisomerase, you could stick it into yeast and it's fine. You can't do the reverse. You can't do the reverse because the human really needs these little modifications to make it live.
So, quick interjection. So, to extrapolate on your lock and key analogy from earlier, are you telling us that this enzyme, these different points that you're showing us here, are each one of those the equivalent of their own lock and key?
To some extent, yes, but it's like you have a master key that can open lots of locks. These phosphorylation marks will modify other. The machine that comes along here and kind of connects to this area, it has to recognize this string here. All right, so that's how it's going to find this in the soup of molecules. Okay, in the cell, it's going to dock to the right location, and it's going to flip the bit, so to speak. And in that sense, it's a lock.
I know it doesn't have to be exact lock and key mechanism, but I guess when I'm going with this, there's just in this one, there's multiple variables that have to be accounted for in order for it to function properly.
Yes, but maybe the way to describe it is these can be configured different ways. So you need a different machine to come along. So you have, just let me explain. You have different cell types in your body, and then you also have different phases of the cell, different cell types, different tissue types. So what happens is, depending on what cell type you have, some of these things will be configured differently. And so these bits are flipped on and off very dynamically. I mean, oh my goodness, I asked Joe, I said, do you think we'll ever be able to measure that? He said, no.
So does this, are some of the things that we are discovering in regards to epigenetic variants in cell types, are some of those things, do they correlate with what you're talking about now on the
yes,
the dynamic nature?
Yes, we call these post-translational modifications on proteins. When they say epigenetics, which has really now become a really bad term because it means different things.
Too broad of a statement.
Yeah, epigenetics is just, I don't like using that term, but to the extent it may involve what they call histone modifications.
Right.
The histones will have diagrams like this. And let me unshare my screen. If I could, while we're talking, I could show a histone diagram, and it will show the epigenetic modifications. So why don't you ask me a question while I bring that up?
I mean, I totally understand where you're coming from on the epigenetic side. I mean, it's becoming. I'm actually reading a book on it right now, and it's extraordinarily fascinating to learn about all of these different variables. And it's like the author of the book I'm reading right now, he's like, epigenetics is a very broad subject, and he like starts creating all these like different subsets. Okay, for this type we're going to call it this, and for this type we're going to call it that. For the reader, and just learning about the dynamic aspects of things that you're showing us right now, of more from a conceptual perspective. You're showing us real world stuff. To me, it really starts to put and you mentioned this briefly earlier, the 4D aspect.
Yep.
Yeah, and to me, when you really start to consider the time variable of these dynamic systems, to me, if somebody's been involved in technology, when I think about dynamic systems, number one, and then hey, I can also have variable modifications based on temporal events that haven't happened yet. I mean, to me, that is just such a mind-bending premise. And then to the point you've been talking about of the structural components, like, yes, these are things that occur, but they require structure, pre-existing structure, to be executed. Is that a fair supposition?
Yes. Is my screen share on?
Not yet.
Let me try to bring it back up.
It started just for a second, then it went back to. There we go.
Oh, there it is. Okay. So this is an example of epigenetic modifications. Again, it's a different convention than the way that I drew it up, but it's the same idea. So DNA wraps around these histones here, and it has this little tail that sticks out, and you can modify pieces of the tail chemically. So you keep the same amino acid, that's a K, that stands for lysine, R is arginine, S is serine, and you have these machines that read, write, and erase the little states here. So that's like dynamic memory right there. So when you're saying, is that like epigenetic memory? Absolutely, yes, that is considered part of epigenetic memory. But the thing that was shocking is that it's, when you learn this, they'll emphasize it's the histone, and histone's only one protein. We're finding out in higher order mammals like humans, all the proteins are like that, almost all of them. They're just full of all these little computational markers. And do
those computational markers you're referring to, are those the? I know there's many of these concepts, but conceptually, are those the different markers that are directly modifying whether or not it's expressed, just to bullet, like from
Yes.
one aspect, but all the way out to a alteration of that sequence if it was expressed without, like a different, it results in a different expression based on those.
Yes, and I can actually identify specifically one because I learned it in grad school. Do you see this H3? That's histone 3, and it's this 27. If that's methylated, if that has that little flick here, it'll change the quality of your skin. That's why the skin at the sole of your feet's different than the skin on your eyelid. If that's modified in the Hox cluster, just that one bit flip, that's how you have different cell. That's associated with why you have different cell types. And I'll show you the machinery that does that. See, now you got me talking about stuff I really like talking about.
Listen, I hope the audience is enjoying this, because if you're not, I don't care, because I'm extraordinarily enjoying this, and y'all can all go away if you don't want to hear this. But as somebody who has been on the layman's level researching these things, I'm really enjoying seeing all this stuff, because it's I've been reading about the conceptual. I've read papers, but being able to actually see the structures of how these things actually end up occurring is, I think, if people don't like this, then you should not be studying biology and learning about these kind of things, because it's, correct me if I'm wrong, but these are the type of things that are at the bleeding edge of biology now. Is that?
It's hard to say what the leading edge now is, because everything's moving. I can't, I feel like if I study things really well, I'm going to be 10 years behind, because there's so many people working now, and billions. It's being driven by cures for diseases. That's why they're pouring money into this. And it's had the unintended, unexpected effect that it's moved forward the intelligent design argument. And I'm trying to look for this polycomb repression complex, and let me just PER. Sorry, I can't. Unlike some people, I can't type and talk at the same time.
Hey,
okay, here I got it. I got
right.
it. I found the image I wanted to show you. It's one of my favorite images. So I'm going to share my screen again, and I'm really glad at least to have someone that wants to talk to me about this stuff. This is the polycomb repression complex. All right, so see that black wire here, that black wire thing? That's DNA. DNA. So we have this link RNA. It's listed as an ncRNA. It's a link RNA that comes from chromosome 12. It goes to chromosome 2. It floats somehow. It navigates through all that Brownian motion. It probably uses the Brownian motion to navigate from chromosome 12 to chromosome 2. it parks in the right gene in the Hox cluster. Okay, so that's how it navigates there is really impressive. It doesn't have active propulsion. So it gets here, and when it gets here, it assembles this complex. It's called the polycomb complex. It's made of all these parts. Now you see all the connections here. This is just kind of a block diagram, but they actually have a very rigid, the interconnections are just insane.
So basically, you're saying they're the absolute perfect shape to be able to fit in to create the correct binding, execute the correct binding and everything of that nature.
Oh yeah, I wouldn't say absolute perfect, but the tolerances are not. They're engineered to very high tolerances. Otherwise, they wouldn't work. So now it docks, and it's going to grab that little histone 3 tail, and it's going to modify that one little bit right there, and that changes the change in the quality of skin between the soles of your feet and the skin on your eyelids.
And is it fair to say that you're talking right now about skin type? Is it fair to say that maybe not all, but a significant percentage of the things that we take for granted in the different types of tissues that make up and enable life are dependent upon, at least from the current observations that are being made? Is it fair to say that things like what you're showing here are required for basically all facets of life as we know it?
For all facets of human life, definitely, and a lot of mammalian life. This was discovered in a fruit fly, this complex. So it's really great that we could study fruit flies to understand human biology. That's what I was saying about the stairway to life. The reason God made these other creatures is so we could study them. It's easier to study a fruit fly and kill it and abuse it than it is to do a human. It's a stairway to understanding that we're fearfully and wonderfully made. So we found the same complex, or a comparable one, inside a fruit fly first, and then we started to see it in humans. I could show you a picture of how well everything has to connect. That same complex, I have a picture of it. Let me find it. And this is also, to me personally, mind-blowing.
While you're looking for that, you were mentioning Brownian motion. I was reading about that a month or so ago in context of how does mRNA get out of the nucleus to the cytoplasm? And they were postulating that in some aspects it's Brownian motion, but then they were looking at some of the other like the miRNAs and siRNAs aren't using Brownian motion and are export proteins, get them and then take them out from the nucleus to the cytoplasm. And then, to your point you're making a minute ago on the complex binding, it's like out in the middle of the cytoplasm and all the chaos that's happening there, somehow the appropriate proteins find it for maturation of these things prior to binding with the mRNA prior to insertion into the ribosome. And when I was thinking through, like looking at those, I know there's like many, many more steps beyond what I just talked about there. I was thinking about that of like, we have all these different dynamic processes being executed separately, then conjoined to execute and come out with a end product that is then modified again by chaperones and other aspects to reach the ultimate end product of whatever the particular protein function is. And to me, just that, when you think about all of those moving parts and processes that have to be in place, and then in regards to what you're talking about on the dynamics of the DNA itself that resulted in that, I mean, I don't know how anyone can come to the conclusion that that does not require foreknowledge of the desired outcome.
It's personally too hard for me to believe. So when Mr. Morgan was asking me what changed my mind, I said maybe I didn't have the best of reasons when I started out. If my screen will share shortly, I hope. I think I have better reasons now, which I'm showing. So I don't know why oh, there. Thank you, praise. this is showing how it has to connect. So these are these colors are either parts of proteins or entire proteins. Can you imagine that all this has to connect to make that complex? You could see how the molecules have to, like you could see it right there, has to connect there, and these things have to connect there. I mean, it may look like a mess, but this is at the molecular level, and you don't have nice shapes. You have spherical circles for the molecules. So this is kind of like when you fill in, the molecule like a kind of a spherical thing with the electrons. On this side, it's the same thing, but it's represented with what they call a Richardson ribbon diagram. You can see how all of these things have to interact. It's just like spaghetti that works really, really well and connects, and it flips it on. So let me just show you structurally what would happen. Let's say you had a deletion. You see this ribbon here, this alpha helix? It's an alpha helix. If you had a deletion there, that's not going to be shaped right anymore. Or if you change the residues, it's not going to be, you won't have that length. That's going to start to fall apart. And these, if you had any of these changes here, it's not going to have that nice ribbony, that we call it the alpha helix shape. So that's why I like structural biology. When someone says, "Oh, random mutation can do that," you could actually say, well, it's going to disrupt this entire complex of how it connects together. And I want to identify parts of the protein. So this protein's like 1,000 amino acids long. They're actually discrete segments that do certain functions. So.
Okay, so I guess this goes back to what we were talking about on the dynamics, right? So you're saying that each one of these different subsections of the sequence that results in this protein have to be specific in order to create the dynamic subfunctions of the protein.
Correct. Now, again, I have to qualify that. It doesn't mean that you can't randomly mutate some parts.
Right. But you're saying that there's sub-functions inside of the overall function.
Oh, absolutely.
So basically, it's like its subroutines are being executed. Is that
I wouldn't use the word subroutines.
For general, not necessarily from a 100% technical perspective. I'm talking for the general audience. A subroutine is that's a term most of us know, right? Is or a subfunction.
I'd say subfunction, and you can actually see the functions outlined here. These are called protein domains. I'm a little more familiar with this is the CXC domain. That's the zinc finger domains. 2 zinc finger domains. Some of these other, they come up. Some scientists will spend their life studying one domain in one protein.
One quick question is, you were talking about the shapes of this. Correct me if I'm wrong on this, because it's been a while since I remember reading something about this. These different parts that are fitting together, the shapes are usually asymmetrical. I forget how I read that was framed. Basically, there's weird little shapes that come off to create the connection points that wouldn't be considered a quote unquote normal chemical reaction to result in those hook points, if you will. Does that make sense? I'm trying to remember exactly how this was phrased in the paper I read a while back.
I'm unfortunately not familiar. I'm not. Maybe if you were lucky enough to find the paper again, you'd be able to. I might be able to answer your question. So I'm sorry.
No, it's okay. I didn't very eloquently explain the point I was trying to make there. I guess kind of where I'm going with all this. I'll put it in a different context. Very often it's attempted to, biology is attempted to be reduced down to purely, cascade effects, deterministic chemistry, right? And I guess where I'm going with all this is, yes, there are chemical or reactions that occur, but these reactions create specific structures which are then combined. to
Yes.
result in the outcome. So yes, there's chemical reactions that happened, but the point I'm trying to make here is from a macro level, yeah, if you welded two pieces of steel together, yes, you could now have X tool. And yes, the welding had a chemical component to it, but doesn't mean that was just a happenstance occurrence in order to result in the tool that was created.
Maybe one way to, as far as the creation evolution controversy, I would actually say the evolutionists are right that there can be sometimes a new tool. Like, it's really easy to make a paperweight. It's really easy. A tornado going through a junkyard can make a paperweight.
Right.
But it's not going to make something very complex. There are examples where I think something can evolve, and you could call it information increase. I actually don't, I don't say that there can't be a change or some improvement, but there comes a point where the system can be so complex that random mutation will not be able to achieve it. I could show you one picture. This is a nice way to visualize protein structure in relation to its protein structure in relation to the spelling of the protein. This is one of the rare cases where you will see the spelling of the protein and also how it relates to protein structure. So I just shared my screen, and I'm sorry to be imposing on all the technical assistance we're getting. God bless you. Thank you. What you have here, let me show another slide. This is the zinc finger protein, and I don't know how many amino acids long it is. It's probably less than 500. Now, if you arrange it, do you see how you have all the C's line up here? Can you see that?
Yep.
And the C's align up there, and then you have like the H's and the H's here. Let me see if I had this in this particular. Oh my goodness, yes, I could show you this. I have this in my. So this is a zinc finger protein. And let me see. So I'll start here. Each of these lines where I have the arrow, each line, each row is a separate zinc finger. And that means it has the protein, that part of the protein will fold like that. Well, actually, it's more like this, but conceptually, you look at that little fold like that. And so let me just page through it. So you actually have, for each row, we have a zinc finger, and that's actually how the protein looks like when it's folded. You could tell proteins fold very differently from one another. And so each of the C's and the H's correspond to that in the zinc finger. So each row builds a little box where that zinc ion can fit. And the reason that's important is that enables that protein to grab to a specific piece of DNA. So this is, again, like a lock and key interaction, so to speak, that you have to program these things, these letters here, so that it's going to grab the right piece of DNA. And so I wanted to show you at least one thing structurally and also chemically and conceptually of how things connect and have to be precise. So if you have about 3 billion base pairs, you can build a zinc finger that's going to go to the right location in 3 billion base pairs. You can build a protein that's going to find it. That's how some of these proteins are able to navigate to that very precise location. So you're reprogramming these parts. And it turns out that a lot of the DNA we thought were junk, like the ERVs and transposons, they are functional, and these proteins dock with those formerly junk DNA. They dock on them, and they create they connect useful machines. See if I have a picture of a machine like that. I thank you for the forbearance. Yeah, there's one machine right there. So you may have an endogenous retrovirus here, and you have one of these zinc finger proteins, a protein that looks kind of like that. And it'll dock right there on the DNA, and it'll connect. This is actually kind of nice. You could actually see how the proteins have to connect. So you have this blue colored protein, part of it connects with the orange and then with the green, and then you have all the other connections here. And it's going to recruit all the machinery that's going to change the little histone tails, and that's how it does computation. So
in line with what you were talking about there about going and finding this specific spot, that's something I've wondered about. I think we take gene expression, or whether it's ERVs, I mean, all these different things you're talking about. I often think we take for granted that occurs, and they actually find it. Do we actually know? Do we have any idea of how? Because to me, when you think about especially from like extracellular signals that are the root starting point of gene expression, like how in the heck, and do we have any idea how, okay, cool, X signal was sent to this cell to express this gene? Like, do we actually know how that happens? Or why?
I talked to a professor that was teaching me this. I said, how does it know that? He said, no one knows. Because I would tell you the suspicion is that it's not in the DNA, it's in the cytoplasm, that they're heritable. There's heritable information, and I don't like using that word, but I'll use it now. There's heritable information in the cytoplasm, and we're only beginning to understand it. We can't really sequence it because if it's stored in the sugars, those are not nice linear molecules like DNA, where you can have a read head just traverse it. Those are like individual pieces, and it's just nuts. I wanted to say one thing. There's a book by Biophysics by William Bialek, and he goes against this bad design argument in a very interesting way. He'll say, yeah, we look very fragile, but there are aspects of biology that are optimized to the limit of physics, so much so that even if we took our best engineers, we could not build it. We could not build it. We can't build like the shark's ability to sense electrical fields at nanovolts per meter. Can't be done by humans, or magnetic fields the way that the birds that are able to navigate 40,000 miles a year. Yes, there's the Arctic tern that flies 40,000 miles a year between the poles, and it can navigate out in the ocean, and it can sense magnetic fields in ways that we can't even build instruments to do that. So when you're asking, do we know? No, we don't. And even if we know how it does it, we probably couldn't build it even if we were given the blueprints. We wouldn't know how to make machines like that.
It's interesting you're talking about the birds and some of these different facets. I've become extraordinarily fascinated by quantum biology and some of the different things that are being discovered in that context, just in the navigation of some of the birds and what they've now. I'm drawing a blank. What's the?
It uses the cryptochrome protein, and
there we go. Yep.
It uses quantum mechanical spin chemistry to be able to sense magnetic fields. I don't know that many chemists are able to build devices that can sense the magnetic field through quantum spin pairs.
Well, I read a book on that. It was very interesting how when that premise was first put forth, there was a whole swath of quantum physicists who dismissed it and said that is completely, you idiot biologists don't have a clue, like that's not possible, and completely dismissed it even being something to pursue. And then a couple scientists ignored them and ended up figuring it out. And then obviously now, as you're talking about, it's now an accepted premise that yes, that is exactly what's happening. And by the way, Sal, just wanted to let you know that we can. I'm greatly enjoying this. I know the audience is, and as long as you want to keep talking, I would love to have you on. I am enjoying this tremendously.
Well, why don't we have another conversation? But can I show you one last thing since I mentioned 4D nucleome?
Absolutely.
4D nucleome is the project is an NIH project. Let me show you their logo here. That's the 4D nucleome. That's connected to the ENCODE project. So evolutionary biologists hated the ENCODE project. Not all of them, but a lot of them, like Dan Grauer. Well, there are follow-ons to that, and one of them is the 4D nucleome, because it shows the importance of the DNA as a structural machine. We've looked at DNA as being a blueprint for proteins. It also is a scaffold. Let me see if I have a picture of a scaffold here. See, okay. So do you see this is a robotic assembly line here? And you see all the little arms? Well, that is reminiscent of what DNA. Do you see these are like little robotic arms, and you put machines or tools there, and it's going to modify and service other machines. But what's really nuts in a good way about the 4D nucleome project is you can have sections. This is called transchromosomal regulation, transchromosomal enhancers and regulation. You have chromosome 2 here, and chromosome 15, chromosome 17, and the X chromosome. There is this FIRRE, this fire link RNA, this little link RNA here that parks in a link RNA, I guess, binding site or close to it. And what it'll do is it's going to draw the chromosome 2 and chromosome 15 and chromosome 17 parts and chromosome X, very specific segments of it, into the right location. And then all these machines, they can co-regulate each other. There are various terms that I don't quite know that there's a distinction. We call them transcription factories, that we can do that, transcription factories. And so that's how they're able to cooperate and regulate each other, and all this chemistry that we don't understand. This configuration here changes between cell types. So you have different arrangements depending on the cell type. That's how it's able to do things.
So are you saying that the based on cell type, the expression of different genes and DNA in general, the same section could vary based on cell type, based on how it's being modified by the transcription factories and factors?
Yes. Or there might be parts, like, let's say in some cell types it'll be silenced here. It won't be this section of chromosome 2 that'll be drawn in. So you can actually reconfigure this, and they know that these things changed between cell types, and they're trying to map it now. So that's why they had the 4D nucleome project. They're trying to see how these different cell factories, how these different transcription factories, or what they call topologically associated domains, change between cell types. This is a different way. We are now looking at DNA not only as, they're talking about, this explains the use of the junk DNA, because all this extra DNA, it acts as spacers, and it also acts as scaffolds and addresses. So for the machine to dock to that DNA, it has to be spelled a certain way, otherwise it's not going to find it. So you want the right machine to go to the right location. And so the spelling of the DNA is very important for how it's going to dock there. So now you see the role. So this may be the gene. The gene may actually only be really, really small. In fact, this isn't to scale, unfortunately. The gene might be way, 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 way smaller, and you have all this quote unquote junk DNA that's there to bring the machines, like a robotic factory here, the tools to bring it into the right position there. And this is what they call cis regulation. This is only within the same chromosome. What you're actually going to have is transchromosomal machines here. And we haven't totally characterized that. I don't think they'll do so in my lifetime anyway. But right. That's why I like structural arguments. You can actually see physically why what may have been called junk DNA is actually useful. You can see it in diagrams like this.
Yeah, a point you were making earlier about the different optimizations of different functions, different things that we couldn't recreate and things of that nature. One of the things that I hear all the time, and it blows my mind, of just like, are you guys not looking at reality? But just the argument that DNA is a crappy storage medium. I hear that all the time. And just, it's, how is this actually storing anything? It's a piece of crap, and not the most efficient way, and things of that nature. And I'm like, okay, we don't even know how it all works. And the things that you're showing make that very obvious.
Yeah.
But we're going to operate from this very myopic perspective that, and where I'm going with this is, it seems to me that the central dogma, number one, has been destroyed and shouldn't even be considered a foundational point in biology. And then if we're going to, it's like almost like humans are just now starting to become cognizant of all of these different facets when we've been stuck in 2 dimensions and it's 4. Is that a fair position to take?
I'd say the central dogma is still correct. I mean, the formal one, where DNA, it codes for proteins, and not necessarily, very rarely, in the other direction. But the idea that DNA is solely to code to provide blueprints for proteins, that's gone. That's gone. DNA does all sorts of things. It's a multi-purpose molecule. It's not just information storage. It has. I talked to a biophysicist recently, a former biophysicist. She said, yeah, what she saw is that DNA is a structural molecule too. So you can see it in diagrams like this. We would call these, I guess these are cis enhancers. Yeah, it provides structure to bring these little dots here are molecular machines. So these these molecular machines will swim inside the nucleus and find that right piece of DNA, and they'll assemble right, and they're going to regulate the gene. All these, there's a lot of computation done. So a lot of what's actually going on is to do a computation to determine whether you have to turn the gene on or off. There's huge amounts of computation. But if you think about it, when actually something as simple as if you, when you're hearing a voice or something, there's actually all these changes going on in the gene. We found that out. It was a very interesting experiment.
In that context, are you referring to, and I know that you hate this word, but are you referring to some of the social epigenetic modifications?
Lots of epigenetic modifications, yes. You'll see it if you Google epigenetic memory. It'll come up with all sorts of different hits. There'll be one where they did an experiment on rats, and they tried to train them, put them through a maze. They did a rather cruel experiment. They beheaded the rats, the one control group, and then they measured the changes, epigenetic, a gross level experiment on the epigenetic changes in their brain cells, and they could see there were modifications at the chromatin level. I don't know how they exactly did that, but that was an impressive study.
Now question for you. We think about this from because we can only see this in, static diagrams and things of that nature. What we're actually talking about right now, all of these things are real-time modifications. I mean, yeah. I know some of them are lifetime long and different, depending on what the kind of modification we're talking about. But the majority of all of this is real-time dynamic reaction. Is that correct?
Right. And we're very lucky.
When I say reaction, I meant reaction and computation or reaction as a result of computation.
Right. So how are they able to elucidate this? They needed some really specialized experiments, like the one that elucidated this one here. That took a team of 20 researchers. They had to be a little bit lucky that they could modify this, and they would have like a luminescent protein that would just attach, and they could actually see then that the segments. And the hope is when you have a luminescent protein attaching here that it's not going to disrupt the function too much, that it could still do this. So there's not 100% proof that we got it right because our instruments may actually interfere with our model, but that's how they do some of these experiments. So there's not going to be any end to opportunities to learn more. This is just like infinitely complex, practically speaking.
Now the
Because there are 100 trillion cells in the human being. It has a different there's only one genome in general, but there are 100 trillion epigenomes.
wow.
Yeah. Yeah.
That's a here's a question for you. So in cellular division, are all of those modifications being passed on like to each daughter cell, or some of them erased, some of them kept, like the
Yes. But if you think about it, it has to be able to do a lot of accounting. So how does a brain cell know how to be different than a liver cell or a skeletal cell? So the cells will signal each other. They'll do a computation and said, oh, I'm this kind of cell. This is how I have to divide for the next generation. And that computation is probably what's going on. And I probably have to go now, but we can, if you want to talk about this more sometime, we can, and I could try to be a little bit more structured if you can suggest what you wanted to talk about.
No, I would absolutely love that. I know everybody's been enjoying this. I've been getting messages of how much people are enjoying listening to this, because now this is the type of thing that people like myself and Standing for Truth and other folks, like, we know some of these things conceptually, but being able to actually have somebody like yourself really explain it, of, I know for myself, the part of my, at this point, I don't even consider it faith. It's okay, well, that's the logical conclusion in terms of what we're talking about, in terms of a creator and God's existence. But for so many folks that don't even have the pittance of knowledge that I have, I think it's very easy to be run over by the arguments from the other side, because until you start to go down these rabbit holes and start looking at what's actually happening, and I know it's not just two rocks banging together and presto, you now have life, and all the different components that are needed. So I greatly appreciate you sharing your knowledge and time with us, and let's do it again.
I actually think that verse where Jesus said, "Seek ye first the kingdom of heaven." Before he said that, he said, "Consider the lilies of the valley; they neither toil nor spin, and yet Solomon in all his glory was not arrayed as one of these." That's prophetic, because that's exactly we're seeing at the biological level. We can't build machines like a simple blade of grass. That would humble all the scientists and engineers together. And so that verse has different meaning for me now that we're studying this. I wanted to give a word of encouragement. You see, we've only had like an hour of conversation on this part of biology, this complexity, the chromatin. People can learn this. You don't have to have a lot of organic chemistry or basic. You can just learn it kind of at the conceptual level, like what we just talked about. And that's one reason I'm writing my booklets. Actually, it's a book project. We're going to write, God willing, several books, because people can actually learn this. Now, the reason it hasn't been taught this way is, there's not been a reason for, like, say, an arts major to study this, but except if it's going to help her faith. And, we can actually teach it without having to teach them organic chemistry and general chemistry and cellular biology. We can especially teach the computer types. The computer types will actually totally get this. So that's why I'm excited. That's why I'm excited to share. So,
awesome. Standing, do you have any final words before we wrap up, or should we go ahead and call it a night?
Thank you, everyone. Thank you. And I hope we meet again.
Mm-hmm.
Well, God bless you all. And Snake, it was very nice meeting you. It was very enjoyable talking to you, and thank you for being so civil. I'm not accustomed to being treated civilly by the other parties, so thank you.
Oh yeah, I mean, I try. Yeah, I had a couple things I wrote down during the whole thing, but I was mostly just taking it in.
Yeah.
I think it'd be interesting one time if we could, maybe even assuming these systems were created by something. Not that I'm convinced, but I think this is a better case than like anti-evolutionism, certainly. But I think it'd be interesting maybe to have assume these systems are created. What now? How do we get to a Christian God or any specific God,
Sure.
really? Because I think that's mainly where a lot of my objections lie.
Sure. Well, I have to make a commercial break. My mom
Yeah.
is in need of me.
Yeah,
So
no
I
problem.
think
So thanks for your time, man. I need to go take care of your
we
mom.
could probably continue another time. God bless you.
Yeah. Have a good one.
Take care.
Peace.